Okay, okay. Can you check now? Yes. Okay. What? Hello? Hello? Do you hear me? Okay. Should we get started? Yeah. Okay. Welcome, everyone. Welcome to the fifth edition of Memory-Centric Computing Workshop. Uh, Yes, I'm Ismail. I'm a PhD student in Safari Research Group. I started in February 2024, so I'm in my third year now. I do research in computer architecture, processing in memory, hardware security, memory robustness, and more. So you can check the website from this link and this QR code as well. So there are some slide materials available already. So you can check during the talk. Is screen share problematic? Yes. It should work. All right. So we have some organizers, me, Nisa, Ataberk, they're PhD students in our group, and we have Geraldo, Zhiheng, and Mohammad as postdocs, senior researcher and lecturer, and we have Professor Onur here. We will have two sessions. The first session will be start with Professor Onur's talk, and then I'll discuss some recent works on processing using memory in real DRAM chips. And then we will have Ataberk and Nisa discussing real prototypes on processing using DRAM, as well as some side channel and cover channel attacks on processing in memory architectures. And the second session, we will start with Professor Phil with fast and energy efficient database using processing in memory. And then we will have three more speakers discussing a wide range of topics related to processing in memory, and hopefully we will be on time and in 6. So we will have another edition of this in ISCA, which will be a full day. You can, if you would like to give a talk, if you would like to do discuss your ongoing work, feel free to submit. And if you cannot make it to ISCA, we will have another one, which will be the 7th edition of this workshop. This one is a bit different. Now, in this one, we will be accepting or evaluating some papers. So if you have ongoing work, again, like some extended abstracts, you can submit your work as a 2-page, and it will be in the proceedings of ICS. So this will be happening in 6th of July on Monday at Belfast, Northern Ireland, United Kingdom. And again, the websites are online, and you can find these slides online as well on the website. Yeah, that's about the logistics, and hope you will have a good time in our workshop. Yes. You can use this.
Okay, thanks. Okay. Hello, everyone. Can people hear me in the back? Okay. My voice is a bit not so good because of the air conditioning in the US, which I haven't been used to in a while. And also the smoke downstairs. I guess before I start, I should say that we should not hold conference in casinos because it really hurts attendance of undergraduate students. A lot of them are considered underage. In a city like Pittsburgh, we have a lot of undergraduate students, and I don't know how many of them decided not to come because they had to deal with this business of dealing with being under 21. I think it's very discriminatory to hold conferences at a place like this. After this statement, it's not a political statement. It's actually a conference-related statement. We're at a conference. And I think we should be including
the business meeting, I assume?
Well, if I attend the business meeting, I would actually say it, but I think we have a larger audience than the business meeting probably over here being online, Yeah, we need to enable the future generation to come to these conferences. I think one of the things that one of my students mentioned actually that I didn't think about was you need to have someone attending the conference to sign off for you if you're under 21. And if someone wants to come to the conference and they know nobody at the conference, this becomes another barrier. And I think we need to be lowering barriers as opposed to creating barriers. Anyway, with that, let me start the talk. So we've been holding these MCCSys. By the way, it's great to be back in Pittsburgh. And I've never been to this casino. I didn't want to be necessarily, but Pittsburgh is great. So I enjoy the greater Pittsburgh. So we've been holding MCCSys for a while right now. We started with real PIM tutorials, which I will flash to you later on. And then we broadened it to memory-centric computing systems. As Ismail said, we'll have 2 more of this coming in 2026. And people are very welcome to participate online, or if you want to present in the next upcoming ones, please let us know. I'll give an overview talk. I don't intend to cover a lot. Please stop me, Ismail, so that we remain on time. And we'll go into more detail with different talks. Professor Phil Gibbons will give a talk in the afternoon. I'd recommend everyone to attend that talk also. And we'll have a lot of fun, hopefully, on memory-centric computing systems. Okay, so this is a short summary of my talk. It's a 1-slide summary. Basically, computing is a huge memory problem today. It has had this memory problem for a long time, but it's becoming even more pressing right now. And memory is really responsible for destroying all of the metrics that we care about, including performance, energy consumption, robustness problems, monetary costs, and hardware real estate. Memory is a big fraction of the hardware real estate, as well as the cost, for example. And this problem is becoming worse with more data-intensive workloads. It's going to become worse and worse, in my opinion. And I believe we can solve it by fundamentally rethinking how we design systems, essentially enabling memory-centric systems. And in this talk, I'm going to talk about 2 different directions of it. One is we've been having a lot of technology scaling issues related to memory. And these technology scaling issues can be more easily solved, and memory can be enabled to be a much better participant in the system if it can autonomously manage itself, as opposed to being managed by a controller that sits on the processor side. That's what happens today. I'm going to talk more about this today because later talks will not cover as much about this. We're going to talk about how to solve some of the memory technology scaling issues by being more memory-centric, by doing more computation in memory. And the second aspect is application and system scaling. The systems and applications are not scaling very well today because of all of these that I mentioned over here. And one of the main reasons is because of the memory bottleneck. And we can actually solve this bottleneck by enabling memory to perform computation. And actually, not just memory, but other devices, other parts of the computing system than just the processor to do computation, and distributing computation across all those parts so that we can actually have a system that can be much more scalable in terms of both performance and energy. This may mean that the system is a little bit more complicated, but it will hopefully be more scalable. So I'm going to talk a little bit about that also, but probably there will be more talks on this topic by Ismail and other folks. Does that sound good? Okay. So now you can sleep because I've summarized the entire talk, and it looks like we're having good weather right now, a little bit. Okay, today computing is bottlenecked by data, and important workloads are all data intensive. They require rapid and efficient processing of large amounts of data, and data is increasing. Basically, we can generate much more data than we can process. That has enabled, for example, the revolution in machine learning because of the availability of data as well as the availability of powerful hardware. And we want to perform more sophisticated analyses on more data, essentially. And you've seen this in machine learning. Essentially, the models are growing exponentially in terms of their memory capacity requirements and as well as compute requirements. Now, there may be algorithmic improvements that can reduce this, but in the end, there will be techniques that will exploit the huge amount of data that we are generating. And I don't think those techniques will go away in the end. We can become more efficient, but in the end, we will keep exploiting this huge amounts of data. Genomics is another domain where we do a lot of work on, and I'm quite fascinated by it. Here, the data growth is even more, actually. You can generate a lot of data because of the availability of these very powerful sequencing devices, like the nanopore sequencing device. And to analyze those genomes, you want really a lot of efficiency. The problem is we have data access is really a major performance energy bottleneck. And unfortunately, our current design principles exacerbate it. Essentially, they cause a lot of energy waste because we move the data from the sensors to the storage, to the memory, to the caches, to the registers, and eventually data gets processed in the registers or buffers that are much farther away from where data is generated or stored. So we waste a lot of energy by moving data back and forth. We also waste a lot of performance by doing that because fundamentally moving data actually is latency intensive. But we realize this performance loss a lot, and we try to fix it by complicating our systems. We have a lot of software as well as hardware techniques that enable heavy levels of multi-threading, for example. Many levels of caching, both in software and hardware. Many levels of prefetching, both in software and hardware. Out-of-order execution, again, both in software and hardware. So our systems become much more complex to tolerate the latencies due to data movement. And this complexity essentially shows itself in terms of power consumption, in terms of energy consumption, in terms of sustainability issues, because our hardware is also more complex than needed, maybe. And also it shows itself as performance loss, because when these techniques that we are designing don't work very well, they're actually adding latency. Many levels of caching, for example. If it doesn't work very well, it's extra latency that you need to go through and your performance degrades. Okay, so basically the problem is all data gets processed in the processor. This comes at a great system cost in a processor-centric system. Let's give some numbers related to this. This is a picture that I wrote when I was at CMU, actually, when I was an assistant professor writing my first NSF proposal, the career proposal, which was actually accepted immediately, let's say. We were looking at scalable and quality of service of our memory systems. If you look at a node like this, there's processing that happens in the cores, but that's only a very small fraction of the system. Most of the system is really dedicated to moving and storing data. And if you actually do the calculations in many systems, it's more than 90%, 95% of a single node. The hardware real estate is dedicated to storing and moving data. Now, it's good to take the perspective of someone who has a blank slate. And I like the example of a 10-year-old kid. If you throw our systems to a 10-year-old kid, will it pass their muster test, let's say? So tell this 10-year-old kid that you're designing this very complicated system. Most of the hardware real estate is dedicated to moving and storing data. Would that be your bottleneck? They will probably tell you something else is probably your bottleneck, not memory. But unfortunately, in our systems, memory is still our bottleneck, even though we're dedicating almost all our resources to it. So maybe we're doing something wrong. So that was hardware real estate. Let's take a look at performance. It's a beautiful paper from Google in 2015 where they analyzed essentially all of their data center workloads according to them on a state-of-the-art Intel system at the time. And they basically showed that most of the time, the processor is waiting for data to come back from memory. The processor is doing what it's supposed to be doing, which is finishing instructions only 10 to 20% of the time. Again, let's be that 10-year-old kid. Ask the question. I'm designing the system. Its sole goal for performance is to finish instructions. It's doing what it's supposed to be doing only 10 to 20% of the time. Is this a good system? They'll be honest with you and they will say, go design something else. Basically fix this, right? Okay, that was performance. Energy is even worse. This is data that I borrow from Bill Daly. These numbers are all scaled right now, but what remains is the disparity between a memory access and compute. And if you look at the disparity in terms of energy consumption of a memory access, a DRAM access, compared to a sophisticated computation operation, it's about 800x over here. If you optimize it, you'll get to 150x, 160x. Below that, it's very tough. So the question is, if there's such a disparity, does it really make sense to move the data to the on-chip caches or on-chip buffers so that you can do computation? Of course, this is not dogma, this is science. Basically, you can do the calculation to figure out how many times you need to reuse the data so that you can amortize the energy cost, energy differential between a memory access and compute, and you'll figure out that it's going to be thousands of times. Okay, and in many workloads, we don't have that much reuse capability. Of course, this is based on some assumptions, but Professor Wenmei Hu from Illinois has very nice analyses on how much reuse do you need to overcome the energy differential. I'd recommend looking at some of his talks. He's at NVIDIA right now. Okay, so that was a complicated arithmetic operation. But today, everybody knows that we don't want to do very complicated arithmetic operations for energy reasons. We want to reduce the complexity. So if you look at a less complicated 32-bit integer operation, the disparity increases to 6400x with these assumptions. And today, we don't even want to do 32-bit operations, right? We want to do ideally 1-bit operations. If we can get away with less than 1 bit, we want to do less than 1-bit operations, right? And that actually increases the disparity because reducing the computation with reduces computation energy more than it reduces the memory energy, unless you're really clever about how to pack your data, etc. So, okay, we're not even talking about storage yet. If you actually think about bringing data from storage, multiply this by at least another 10x. And then ask the question to your 10-year-old kid, am I doing the right thing with this disparity? I think they will go crazy. 64,000x? Are you crazy? Are you moving every data to the processor with 64,000x? Okay, so we tried to do a lot of analyses on workloads to understand the impact of data movement and memory on performance and energy. In this work with Google, it was an ASPLOS 8 years ago, where we analyzed the mobile workloads that Google had at the time, TensorFlow inference, for example, Chrome browser, and also video encoding and decoding. And on average use cases, we found out that more than 60% of the total system energy in mobile systems is spent on moving data across the memory hierarchy. This is average use cases. Worst cases are much worse, of course. Now, we repeated this study more recently using the edge TPU, again with Google, looking at machine learning models, edge machine learning models running on edge TPU. This is before LLMs. So LLMs actually worsen this. I will show you some data from LLMs later. But we found out that on proprietary edge neural networks that are executed on an edge TPU, more than 90% of the total system energy is spent in memory, in large ones. At the time we tested, the large ones were LSTMs and transducers, and you can see that most of the energy is in DRAM and off-chip interconnect. And if you actually push computation to the memory side, which I will discuss later on, you can reduce that by about 5x or so. Okay, so basically we have a problem, which is processing of data is performed far away from the data, and we can solve it by being more fundamental about it. Of course, we can patch it also, which is what we've been doing, patching the processor-centric system. And we should be doing that, no question about that. But we should also be investigating ways to become more fundamentally efficient by minimizing data movement, computing where it makes sense, where data resides, essentially having a more data-centric approach to computation. And there are many places where we're not doing computation today. We're limiting computation to a very small fraction of this SRAM-dominated chip. We're not even doing computation in most of this chip. Most of this chip is SRAM and buffers, and those buffers and SRAM can be doing computation on the data that they have. We want to do computation here in storage, sensors, essentially everywhere. Of course, this is easier said than done, but if we can enable that, we can figure out where to do the computation in the best way based on some metrics that we want to optimize for, and we can design our system in hopefully a much better way, in a distributed way, to enable this. In the rest of the talk, I'm going to talk about memory as an accelerator, or memory as something that can do things on its own. And we know how to design accelerators. We have a lot of compute-centric accelerators today, processor-centric, I would call them. They're sitting on the other side of the memory bus. Why don't we design some accelerators that are sitting on the memory side of the memory bus? This can actually reduce the data moment across that bus. And this can also enable us to use the programming paradigms that we have developed for accelerators, which is at least easier to adopt. Okay, so this is a huge slide with lots of questions. I think there are a lot of questions that are waiting to be researched in this area, and it's fascinating. This is an across-the-stack problem. Essentially, we would like memory to do operations. We would like to communicate with memory to supply those operations to memory in the accelerator model. and we would like to get the results. Then the question becomes, how do you design the compute-capable memory and the controllers? How do you design the processors and communication units? How do you rethink the processors and accelerators that we have today after you have computation capability on the memory side? How do you design the software and hardware interfaces to enable this and enable this efficiently? How do you design the system software compilers and languages to make this easier for the masses to adopt? And how do you rethink the algorithms to match the computation capability that you have or that you have put into your memory and storage devices? And I think my favorite, which I'm not working on, is the theoretical foundations of computing. A lot of theory, essentially the theory of computing is based on some very processor-centric assumptions, right? When you actually analyze the complexity of algorithms, you use essentially big O, big theta notations, and these are counting operations. But maybe they don't matter in today's world that much. Maybe we should be really optimizing for data movement along with operational complexity together. Okay, so there's a lot of exciting research that can be done across the stack, all the way from devices to algorithms. Okay, I should also say that this is not a new idea. People have proposed this idea since 1960s. These are the earliest papers that I could find on the topic. I'm happy to update my slides if you have newer papers. These folks imagined putting logic near memory. I'm going to distinguish between logic near memory and logic using memory later on. But they actually added logic near memory for various reasons, including cost. This is a beautiful paper from Harold Stone in 1970. And a lot of people have looked at the idea over many decades. The question is, why is it interesting today? I think today we have nowhere to escape, meaning we have all these bottlenecks that we discussed. And at the same time, we cannot really trade off between performance, energy, and sustainability. We want to improve performance, improve energy consumption, improve sustainability, all at the same time. And I think we can improve all metrics by actually designing much more data-centric systems. So at the application and system side and the user side, we're really pushed by them, as well as the requirements, to do something different. At the lower sides, device and technology sides, we're also being pushed to do something different because memory technology scaling, especially DRAM technology scaling, has not been going well. There are issues like row hammer. You can induce bit flips in commodity DRAM chips very easily. And many scaling issues can be solved by adding more computation capability on the memory side or the memory controllers. And this actually is a different way of doing computation in memory for a different reason. But once you start doing computation in memory to scale the memory technology, you can use the same computation capability, or you can add more computation capability to actually accelerate applications as well. And there are also some emerging technologies that can enable new functions in memory that many people have not thought about 60 years ago, for example. So I think we're kind of squeezed in the middle. And that's why people are also interested in building memory-centric systems. Yes, please. Sure, yes, please.
Because of GPUs and other accelerators, there's much more of a community acceptance that we have to do things that are more exotic.
Okay, yeah, I like that. Yeah, sure.
Like we're no longer in a world where like everybody's, I only want a whole bunch of CPUs and nothing else.
Okay, yeah. I will probably add that to the maybe mindset part, which is our optimization points are changing basically, as opposed to doing the same thing. Yeah. Although not everybody may agree in the industry. Yeah, that's the downside. Okay, great. Any other questions, thoughts? Okay, so what I'm going to do in the rest of the talk is I'm going to talk about technology scaling because we're not, other talks will not cover as much of this one. But I believe this is also important because today we can actually push computation inside the DRAM chip to protect DRAM. If we can actually use that opportunity to push more computation, why not, right? So in my group, we've been building a lot of infrastructure to test the technology scaling issues, DRAM scaling, as well as flash scaling. I'm not going to talk about flash. I'm going to focus on DRAM. And we built FPGA-based infrastructures to test memory. This is the HBM infrastructure that we have. The previous one was DDR4. And we have a laboratory at ETH with more than 100 FPGAs where we can test. Ismail has worked on that quite frequently. And we're expanding it. And the reason we built this to really understand the technology scaling characteristics like retention problems or row hammer problems. This was the infrastructure at CMU when I was at CMU, where we did a lot of row hammer testing. And this was the original infrastructure that we built in 2011. And we open sourced these infrastructures, SoftMC, DRAM vendor, and we're happy to work with the community if they're interested in using these infrastructures for whatever purpose they deem could be useful, including technology scaling issues. And yesterday we did have a tutorial on DRAM vendor and Ramulator, which Nisa was leading over here. So if you're interested, you can find online. But But basically, using this sort of FPGA-based infrastructure, you can study issues like row hammer. How many people here know about row hammer? Okay, how many people do not know? Don't be shy. Okay, I see one hand at least. So I'll go through it relatively quickly because most people know. But this is the fact that you can induce a bit flip in DRAM while being perfectly legal, meaning doing nothing illegal, by repeatedly accessing a row, activating, pre-charging, activating, pre-charging, activating, pre-charging, opening, closing, opening, closing, opening, closing. You apply high voltage and low voltage repeatedly to a word line. And if you do this repeatedly, enough times before the cells get refreshed, the rows, some cells that are adjacent to the cells in these rows get corrupt. We call this the hammered row, we call this the victim row. This happens because cells are too close to each other and cells are too small. Whenever you activate one row, you apply voltage, and that voltage and the electric field that you have over there induces noise in nearby cells. And if you do this repeatedly, that noise actually causes electron injection and electron escapes as a result. If you do it enough times, you may actually deplete the electrons that you have in a particular cell, getting silent data corruption, basically. So you could do this in real chips, and this is becoming worse. As the cells become smaller and closer to each other, and our lab measurements show that the vulnerability has increased by more than 100x over the course of 10 years or so. Okay, this is the original paper. If you're interested, you can read more. We also said that this is a security problem, and in the security community, a lot of folks showed that you can actually, because you can induce these bit flips predictably, and as a result, you can do a lot of interesting attacks. And I'm not going to talk about these because it's not a row hammer talk, but if you look at Usenix security last year, there were 7 papers on row hammer, including one that did attacks on DDR5, another one that did attacks on GPUs. Okay, we wrote a lot of papers on this topic. This is not the only problem that we have in DRAM today. You could actually make things much worse, meaning there are other read disturbance problems that we have in DRAM, like row press. This is something that we discovered more recently in ISCA 2023. And here, instead of activating a row at the maximum possible rate, like row hammer does, you activate the row and keep it open for some time. And if you do it, you induce a lot more disturbance, a different kind of disturbance to adjacent rows. And then you don't need to activate the row as many times. So you can reduce the number of activations to induce a bit flip by 1 to 2 orders of magnitude, meaning things are much more vulnerable with this read disturbance effect. And the solutions that you have for row hammer don't work for row press. Okay, these are results from our real papers for all manufacturers, basically. All manufacturers' chips are vulnerable to these problems. So how do you solve this? And why am I telling you these? I could keep talking about a lot of these, but basically, we've always argued that to solve these problems, you need to have intelligent controls, meaning computation capability inside the DRAM or controllers to figure out that something that would lead to an error or that would lead to a failure is going on. You want to detect it early, and you want to take mitigating actions such that that bit flip or silent data corruption does not happen. And we wrote papers about it. The good news is industries actually picked it up, and they have actually implemented DRAM chips with this sort of controller in it. This is a paper from SK Hynix in ISSCC several years ago, 3 years ago, where they acknowledged the row hammer problem, and they described their solution, which is per row hammer tracking. Every row, they added an activation counter to every row in DRAM. This is a lot of cost, actually, if you think about it. And whenever a row is activated, its activation counter is incremented. And if the activation counter is greater than some threshold that they determine, then they take some mitigating action, like refreshing part of DRAM and part of some of the adjacent rows. They don't talk exactly how they do it, but that's the general idea. So basically, they have some computation logic that they added to DRAM, including some metadata to support the solution. And this is real DRAM chips. This is standardized by JEDEC a couple of years ago in 2024. Finally, the good news is this is actually, some folks in industry have said this is the biggest change that has happened to DRAM in the last 20, 30 years. I kind of agree. It could be, it's called per row activation counter, which is essentially what I just described. In my opinion, this is not the best solution you can have, but you can argue whether the solution itself is good or bad, but the solution direction is more memory-centric. Right now, the DRAM chip actually does computation, manages itself, etc. So I think the solution is a good direction. People are being more memory-centric, adding computation to the DRAM chips. The question, of course, is our solutions good? You don't need to be a 10-year-old kid to figure out that the solution is not a good solution to the problem it's presumably trying to solve, right? So we have done a lot of analyses on the solutions, and it basically requires a lot of care to get it correct. And if you want to actually reduce the performance overheads and energy overheads of the proposed solutions, you need to be a lot more careful, and you need to make the controllers a lot more intelligent. Basically, intelligence on the memory side should increase for better solutions. Okay, the question always is, can we do better? And I think one of the issues with this, let's say, DRAM handling its own rowhammer mitigation is today's memory interfaces don't allow DRAM to operate autonomously. And JEDEC actually tried to keep that. Unfortunately, it's not very nice because you can run into situations where DRAM needs more time. And we have proposed a much better interface, in our opinion, a memory-centric interface called self-managing DRAM. The idea is, I think we need to change the memory interface so that we can actually be more memory-centric and also give breathing room to the DRAM chip to do its own operations. So for example, the DRAM chip inside this machine and in my pocket right now cannot do anything by itself. It's receiving a refresh command every 7.8 microseconds from the memory controller that's on the CPU or GPU. And basically, it's getting refreshed. The memory controller is saying, refresh, refresh, refresh yourself, refresh yourself, refresh yourself. I'll keep sounding stupid if I do it every 7.8 microseconds. In HBM, it's 3.9 microseconds. Basically, the DRAM chip cannot do anything by itself, even refresh. And the idea that we had was, can we actually change the interface minimally such that we can enable some breathing room to the DRAM chip, such that DRAM chip can do these operations without requiring controller to dictate them. And this will also enable other benefits, like DRAM manufacturers can implement optimizations internally without requiring changes to the interface or change to the memory controller. So this can enable actually DRAM chips to evolve and become better without going through JEDEC, essentially. So the idea is very simple. If the memory controller sends an activation command to a DRAM chip, and the DRAM chip is busy in that particular region, the DRAM chip says, sorry, memory controller, I cannot honor your request, try again. It's essentially a negative acknowledgement. And the DRAM chip can do it at fine granularity. It doesn't need to block the entire DRAM chip. It can block a small portion. And we've shown that by doing this, you can enable a lot of optimizations that people have proposed, and you can enable new optimizations and make the system much more efficient. And you can actually enable new ideas to be developed on the DRAM side without requiring changes to the processor or the interface. So I think there's a lot more to do in this area. We should be thinking new interfaces. And I think processing in memory is really important to think about new interfaces because it's difficult to do things if you don't have new interfaces. Okay, so there's more to come. I will conclude this part very quickly, but essentially there's a lot we don't know about DRAM still. This technology has been around for 60 plus years, and we're learning about it. We're discovering new things about it. For example, aging. This is something that I cannot claim we understood very well, and we need to understand this more. That's why we need to test things with our infrastructure. We've discovered in the last year issues like variable read disturbance, which is the fact that read disturbance threshold of a row changes randomly and unpredictably over time. So if you actually configure your row hammer and row press defenses today, they may not be very good defenses 5 days down the road, let alone 5 years down the road, because this threshold changes. So you need even more intelligent controllers, we argued, based on this. And you can take a look at this HPCA paper. There's a lot of data, a lot of analysis. We pushed out another paper to archive called Discord to try to figure out how this works. And some of these actually, we don't know the underlying causes. We can speculate because there are no device level understanding. The lab we built actually enables some new thing to be discovered at the system level. And later, device level folks explain it. This happened multiple times in our studies. So we'd like some device level folks to explain this one also. Ismail, who is sitting over here, has discovered that there are even worse issues than row hammer in DRAM, except they're not as bad right now. But if DRAM keeps scaling, they're going to be much worse. And this is the idea of column disturb. A single row activation can actually cause disturbance across all of the columns the cells are connected to. And this is thousands of cells, thousands of rows. Existing row hammer defenses don't work with this, so you need different defenses to fix this problem. And if this problem is not fixed, it may become as bad as row hammer. So our goal is to actually fix these problems early on. But all of these problems, the fixing requires more and more intelligence on the memory side, more and more computation, more and more tracking on the memory side. And again, Ismail has, maybe he's going to talk about this, but at least he's going to talk about processing using DRAM. He's also shown using our infrastructure that read disturbance becomes much worse if you're doing processing using DRAM operations. And I'll let him to discuss that more because I don't have time. You may say that other technologies fix these issues. I respectfully disagree. Unfortunately, all other technologies like phase change memory, STT-MRAM, whatever your favorite technology is, they have some reliability issues that require intelligent controllers. In fact, some of them are much worse than DRAM. For example, phase change memory, we've done a lot of work on PCM and STT-MRAM. And unfortunately, they require mechanisms for write management and wear leveling because they wear out after some number of writes. Right? So immediately you need an intelligent controller, just like Flash. And I think none of these technologies have scaled to the dimensions that we've scaled DRAM today into. If they actually scale to those dimensions, they will have a lot more issues than they are visible today. And people have clearly reported a lot of write disturbance, read disturbance type of issues in the memories also. Okay, so that's why we keep building our laboratory. Hopefully we'll have more and more discoveries, and we'd be happy to help other people to build if they're interested. Now I'm going to skip these. There's a lot of work that are really interesting, but we don't have time for it. There's actually work coming up at ASPLOS as well. But if you're really interested, we have a tutorial on DRAM Bender and Ramulator that we had. And there's going to be one more tutorial at ISCA, so you haven't missed anything. We cover some of these issues. And I think also ICS, right? So Nisa and Ismail are going to travel and hold two different tutorials at 2 different conferences. Okay, any questions? I covered a lot of technology scaling. Hopefully I didn't cause any bit flips. Okay, so let me jump into more, essentially the second part, which is enabling application and system scaling by doing computation, offloading computation into memory. And I think there are 2 types over here. Fundamentally, the nature of processing, I call everything processing in memory. People called logic in memory in the past. Fundamentally, there are 2 types of processing in memory. Processing near memory and processing using memory. And these differ in how they treat logic. Basically, you have logic and you have memory. The way we design systems today is by coupling logic and memory at some distance. And processing near memory says, put the logic closer and closer to memory. You can put it next to each cell. You can put it next to the row buffer. You can put it next to each subarray. You can put it outside the bank, like a lot of people are doing. You can put it somewhere inside the DRAM chip, basically. But logic is designed completely separately than memory like we do today. Today, you have even different fabrication technologies, very different compilation flows, etc. Testing flows, they're all very different between logic and memory. Processing using memory is fundamentally different. You have logic and memory. Forget about logic in processing using memory. I have memory only. I don't design extra logic. I treat this memory as logic, meaning any memory has some fundamental analog operational properties that enable it to do computation, meaning logic. And I want to figure out what it can do, and I want to use that capability to do computation. So I don't add extra logic over here. And this is fundamentally more efficient in the end, but you may be limited in terms of what kind of operations you can do, because that is dependent on the memory technology right now. And in the end, I think we need to combine both because they have different characteristics. With processing near memory, you can have a lot more complicated operations more easily because you're designing logic for that purpose. With processing using memory, you can be a lot more parallel because every cell can be actually performing some sort of computation that it's actually very good at because of its analog operational properties. And partitioning work across these is very nice. Now, given that this doesn't change the paradigm as much, meaning you have logic and memory, you still design logic and memory separately. This is easier to do. This is much harder to do. But I think I'll show you results that Ismail will show you results that even existing DRAM chips, even if you do nothing to the DRAM chip, if you change the timing parameters, violate the timing parameters, you can see the computation capability in existing DRAM chips based on our real results. Existing DRAM chips can do essentially all types of bulk bitwise logic operations, including copying and initialization. Okay, so I'll start with processing near memory, and then let's see how much time we have until processing using memory. But you intend to cover processing using memory, right? Mostly. So if I don't cover a lot of processing using memory, you're in good hands because Ismail has done a lot of work in this area. Okay, let me cover processing near memory. So this is something that's already happening, actually. There are attempts. We worked a lot with the UpMem company, which actually had a DRAM design where next to each bank, you have a complete general purpose processor, multiple instruction, multiple data, multi-threaded processor, and you have a reasonably easy programming mechanism, some compilation mechanisms, which could be improved, of course. But we tested a lot of workloads on the system. And I think Phil is going to talk a lot about UpMem, so I'm not going to talk about UpMem, frankly. But in the original versions of our real PIM systems, we actually talk a lot about UpMem, their architecture. They were bought by Qualcomm more recently, so they don't exist anymore. But hopefully Qualcomm will do something good with it. Let's see, I guess. So there are also other companies that also added logic next to each bank, Samsung, SK Hynix, Alibaba, so that they can perform more limited operations. These are more specialized accelerators. They can perform multiply and accumulate operations, for example, or recommendation system operations in a Alibaba case. But essentially, they're adding logic next to each bank in some way. There are also some other near memory processors where you can have an FPGA over here on board and a lot of memory attached next to it. So this is also a near memory system, processing system. This could also be a near memory processing system. You have a logic layer underneath memory layers. I'm going to talk about some example works that we have done in near memory processing, but I think this is an area that's getting easier and easier, hopefully, by industry. And as Phil said, the industry's thinking, hopefully, is also evolving so that they're open to other approaches than just doing GPUs or doing business as usual. Let's see. So with CXL type of interconnects, for example, you can offload computation to other devices more easily. That's good, I think. Having more flexible interconnects helps offloading. I'm going to talk about some of the work that we've been doing. I think 3D stacked memories are actually very interesting and very important. They can enable processing near memory more easily by tightly integrating logic and memory together. Essentially, you can have a nice, clean logic layer that's designed with a logic process. So you can put a very good accelerator or processor over here that has low latency, high bandwidth, low energy access to many memory layers, let's say. And today, I think we're somewhere in the development. There's TSVs, there's hybrid bonding. Going forward, there'll be more monolithic 3D technologies where things can be connected with much wider, much more higher bandwidth connections like vias as opposed to through silicon vias. So I think there's a lot more opportunity over here. And when we first started looking at something like this, we assumed a good logic layer. This is a paper that we published about 10 years ago at ISCA. I'll go through it relatively quickly, the basic idea. We basically said that we wanted to accelerate graph processing. Maybe we should have focused on machine learning at the time, but graph processing is also interesting and important from my perspective. You can combine machine learning and graph processing also. But basically, the idea is graph processing is very intensive in terms of data movement, not as intensive in terms of computation. The idea is to have an array of in-order cores inside the logic layer. These in-order cores can communicate with each other, and each in-order core stores a portion of the graph on top of itself, basically on the memory stack that it owns, let's say. And this is a remote procedure call, remote function call based programming system, meaning if you actually want to do some operation on a data, you ship the function to the data as opposed to move the data to the function. And essentially, that's what we did. If you want to update a graph node, you send the function and the temporary values that you want to update with to the core that owns that graph node. So we had this remote function call based programming model. Of course, one cube is not enough because this is maybe 32 gigabytes, maybe 64 today, maybe even higher today, but still not enough for large scale graph processing. So we had a distributed system of these cubes that are connected via some network. And we partitioned the graph on top of this so that hopefully you minimize the communication across the chip edges over here. And you keep data as local as possible within a chip and within a core as much as possible. So that's the idea. Other people have developed more than what we optimized for, so the results that we have today is better. But this is essentially a near memory processing-based distributed system. All of the other systems that we compared to at the time were processor-centric, so they have the processor-memory distinction and dichotomy, whereas here you have a distributed system of near memory processors connected to each other somehow. And we were able to get 8 terabytes per second bandwidth available to all those 512 cores at that time. Even today, this is a big number, but numbers are much bigger today, of course, right? And we showed significant performance improvements averaged across multiple graph processing algorithms and also energy reductions at the same time. So you can improve both performance and energy, let's say, by an order of magnitude. And we didn't optimize the system. There's more work that's built on our work that increased those numbers to 100x on both sides. Okay, so I think there's more work to do in this area. I'm going to skip this one, but you can actually optimize the algorithms even more, change the ISA, and you can get even better results. Let me talk about machine learning, and let me talk about not modifying the system as much, because we kind of assumed we have a lot of freedom in the previous one. But what if you don't have a lot of freedom, and you want to actually accelerate some machine learning workloads without changing the workloads that much without requiring a new programming model. So we did this work with Google a few years ago. And this is what I mentioned earlier, but we analyzed Google's edge neural networks executing on the edge TPU at the time. And we found out there is a huge heterogeneity in terms of characteristics of different models and different layers. If you look over here on the x-axis, we show the parameter footprint of different layers, different models, and we show the arithmetic intensity. You can see that some layers have very small parameter footprint and very high arithmetic intensity, whereas some layers have exactly the opposite. And we argued that having a single accelerator that's processor-centric is not able to cater well to these layers, so you want to have heterogeneous accelerators. So that was one example. There's also, if you look inside a model, this is a convolutional neural network that Google used to use, I guess. I don't know if they still use it, but there's a huge variation across different layers in terms of arithmetic intensity, as well as multiply and accumulate operations. So we basically said that we don't want to have a single monolithic accelerator because it's not good at catering to all of those. We want to have a heterogeneous set of accelerators that are designed for different types of, let's say, bottlenecks. If your workload is if your layer is very compute intensive, it can be accelerated using something like this, but a smaller version of this, because now only compute intensive layers go over here. So you have a compute-centric accelerator designed for only compute-intensive layers, not memory-intensive layers. If your layers are memory-intensive, they get accelerated in the logic layer of 3D stack DRAM, and we have two different kinds of accelerators over here. The details are in the paper. They're optimized for different layers and different data flows that you have in different layers. We could have had it 4, 5, etc., but we stopped at 3 for complexity reasons. And the idea is you need to have a software. Okay, I didn't talk about it. You need to have a software mechanism that distributes the tasks or layers to different accelerators. And we could have done a better job over here if you wanted to improve performance even more, I think. That becomes your bottleneck at some point. And so you need to have a clustering mechanism to decide what layer goes where based on the characteristics that you collect online or offline, depending on what your workload is. But in the end, we showed that on average, across the models that we examined at Google, you can reduce energy consumption by about 3x. And you can also improve inference throughput by about 3x. You can also improve latency. These numbers are smaller, of course, but here we're not changing the system. Basically, the workloads are exactly the same. We're just adding another runtime layer to distribute the work to heterogeneous accelerators. We're not changing the programming model, for example. The software is exactly the same. Okay, so you can do function offloading or layer offloading this way. Okay, maybe I'll cover a couple more things and then stop for questions. So more recently, we've examined, of course, large language models like everyone is doing, and especially with speculative decoding, etc. I will not go through these in detail. These were published in last ASPLOS. But the key takeaway from my perspective is the same. You have different parts of an LLM system, and different parts require different types of accelerators. Some of them are extremely memory intensive, so you want to go actually have a memory-centric accelerator. So this is the accelerator in the end. There are some parts that are really compute intensive, like fully connected layers that have huge computation intensity. We keep them in the high performance processing units, which could be a GPU or a TPU type processing unit. There are some parts of fully connected layers that are not as compute intensive. They're more memory intensive, but they also have a lot of computation. We figured out that you can actually design a near memory processor with near each bank, you actually have acceleration capability. And this acceleration capability needs to be a lot more than, for example, what Samsung, I guess what they call PIM-DRAM provides. So you actually have a lot more computation capability near banks over here. And then there are some layers that require a lot of memory capacity. These are attention layers, for example, KV caches, huge memory capacity, and also they are less compute intensive. So we disaggregate them across the interconnect so that they can have a lot of capacity and also some computation capability next to each bank. Now, not as much as the fully connected layers. And we show that compared to best prior system, which was another processing in memory enabled system, actually, you get better speed up and better energy efficiency increase by adding this sort of heterogeneity. Okay, there's a lot in these papers, so I'm just giving you a high-level overview. The details are in the papers, of course, and I'm happy to take any questions. In some other work, we tried to actually eliminate the GPUs completely by taking advantage of the CXL interface communication primitives, as well as computation capability inside the DRAM. So this is similar to SK Hynix's GDDR6 PIM, which can do multiply and accumulate operations. So we put the matrix vector multiplications over here, And other more complex computation go to the processing near memory logic that we design inside the CXL device. But we basically don't rely on GPUs or TPUs in this particular case. And our goal was to show that you can design a system that can outperform and be less costly than GPUs. This requires 32 CXL devices in this particular case, but you can, of course, change that. And we showed that by designing a system like this and by changing the communication primitives that you have in CXL, you can do better than an LLM inference system that incorporates only GPUs, and you can be also cheaper. Okay, that's the idea. This is also open source, so you can actually, if you're interested, you can build on it. So there's more that I can talk about in processing near memory. We did a lot of work on bioinformatics acceleration and also storage. I think storage I didn't talk about, and I don't intend to talk about today, but as your data sets grow, DRAM becomes too expensive. And with genomics, for example, we have a huge explosion problem in terms of data sets. If you're doing, for example, genomic analysis on hundreds of terabytes, you don't want to do it in DRAM. You really want to do it in storage. And storage system is a great place where you can accelerate computation because it has DRAM as well. In fact, storage system is a system by itself. So you can essentially build everything over there. So we've done works in that area. I don't know if there are any talks today on storage, but maybe in the longer version of MCCSys at ISCA and ICS. So yeah, there's more to do in the storage. And we've accelerated retrieval augmented generation storage also, but I'm not going to talk about that. There are many other examples in this paper that we desperately need to update. Last time we updated was February. It's already 100 pages or so, but there's more to add to this. And if you have any feedback, we're happy to actually get feedback. The good news is there's a lot going on in this area. Our goal was to actually describe, give a fresh perspective, modern perspective on processing in memory, cover the reasons why today it's more interesting, also cover old works, but also as much as possible cover existing works. But the downside is there's so much work going on in processing in memory today that it's very hard to keep this updated. But hopefully this could give you a place to start from if you're interested in going into this area. And yeah. And we're happy to get feedback, of course. If you have any feedback, if we missed some prior work, for example, it's good to let us know. Okay, any questions? I've covered processing near memory. Yes.
The question I get asked, I've done this, the measurements that you've done, you're still expending the memory, the energy to get the data out of the DRAM, even if you're only going to on-bank core.
That's correct, but not outside the DRAM chip.
Right.
Yeah.
So what fraction of the energy remains behind?
Yeah.
All the data movement energy, but
yes.
fraction of energy remains behind just the
yeah. Okay, Ataberk, do you have the answer? I think basically the high level is sorry, the most of the energy is really outside the chip, but maybe you have an answer number from the sector DRAM, for example. Maybe not off the top of your head. Sorry, I put him on the spot, but so I think the most of the energy is really on the outside the chip. Yeah. You're really driving these things, but exact fraction. Yeah, sure. Yeah, I think I'll ask Ataberk, but we can investigate and we can get that. Because so what people have done, the reason I point to Ataberk is because he's done work on fine-grained DRAM, meaning reducing the width of the DRAM, both outside the chip as well as inside the chip. And there should be some numbers that we have. It may be older technology, but yeah. Okay. Any other questions? Yes.
Quite confident high level how general work is offloaded at some sort of higher level.
Okay. Maybe Phil is going to explain a little bit of that, so I don't want to. Yeah, because okay. I'll let Phil talk about that. Does that sound good? Okay. If you're not patient, you can go and look at the older tutorials where we describe it to death, let's say. But I think Phil, yeah, I'm looking forward to Phil's talk also. Okay, any other questions? Okay, how much time do we have? I'll pace myself. 5 minutes, okay, I can do in 5 minutes, sure. I don't intend to cover everything, but I'm going to cover processing using memory so that Ismail can take over. As I said, this is fundamentally different. And processing near memory, this was proposed in 1960s. but processing using memory is a little bit harder to see in literature. This really, people who were doing memristors proposed in 2008s, 2010s, for example. We were doing DRAM, and we were proposing things like that in DRAM. It's not clear that this was done much earlier, because we're really exploiting the analog operational characteristics of a memory technology. It's not necessarily analog computation, because internally you can actually represent things in a digital way. Okay, basically I'm going to talk about some of the works that we've done processing using DRAM. Essentially, you can do a lot of things with DRAM. Using its operational characteristics, which is essentially chart sharing, you can do bulk bitwise copying, initialization, zeroing, bulk bitwise AND or NOT, majority NOR NAND. You can generate true random numbers by You can have physical unclonable functions. If you want to do a more complex computation, you can treat DRAM as lookup tables, and you can do lookup table-based computation. Most of these come at low cost. Lookup tables are a bit more expensive. And the key idea is to use analog computational capability of DRAM. And the basic idea is to activate multiple rows, either in sequence, in quick succession, or concurrently. If you do it in quick succession, you copy one row to another, if they're in the same subarray. If you do it concurrently, if you concurrently activate multiple rows, you get computation capability, bitwise majority function, for example, or some other function, as we will see. And the fascinating part over here is, like we did a lot of work together with Phil, Vivek, for example, led a lot of this work. We showed a lot of things in simulation that this is doable, and the circuit theory is good, great. And more recently, we've shown that by violating the timing parameters in real DRAM chips, you get all of these functions that the circuit theory predicts exist. Okay, so you get significant performance energy improvements that I will not go into right now. Are you going to talk about some of these? Or? Okay, so maybe not cloning. Okay, maybe I'll start with cloning, because it's probably the simplest thing you can do. The idea is, if you want to copy this white page to this gray page, today you have to go through the processor, basically. You copy byte by byte all the way to the caches, or at least to the memory controller if you set up a DMA. And then you copy the entire page over here, and then write back the data to memory. Essentially, you cause a lot of data movement. Again, if you take the head of a 10-year-old kid and give this picture to a 10-year-old kid, it's good to do this experiment probably with a lot of 10-year-old kids to see what they come up with. I'm hoping what they would come up with is, don't do that. Why not just do this? They're so close to each other, right? So basically, the idea is that move data from one location to another location without involving the processor going through the CPU. Yeah, and this has a lot of benefits. I'll show you in the best case, the source and destination pages or rows are in the same DRAM subarray. And the idea is to first activate the source row, which brings the data into the row buffer. Now the data is strong in the row buffer. And in quick succession, you activate the destination row, which implicitly deactivates the source row and connects the row buffer to the destination row. And essentially, you copied the source row to the destination row through the row buffer this way. This is the fastest way we could come up with to do this copy in DRAM without modifying the DRAM structure. Okay, and this is negligible hardware cost in our original row clone paper, and you can get significant performance and energy improvements. Of course, we have proposed mechanisms to do this interbank and inter-subarray, etc., but I'm not going to talk about that. Later works improved some of these things also. So that's row clone. What is computation? Computation is essentially, in row clone, we sequentially activated rows. And later work, actually, there's a work in Micro 2019, Compute DRAM, that showed that violating the timing parameters, you can actually get row clone in real DRAM chips. So you don't need to actually change the DRAM chip. And later work from Ismail showed that you can actually get it almost perfectly reliably. And you can do that not only from one row to another row, you can copy one row to 31 other rows almost perfectly reliably. He's going to talk about that, I think. Yeah. So let me talk about computation, and then I'm going to stop, I think. Basically, if you want to do computation, assume that these are 3 rows that you have in a large subarray. This is a sense amplifier. If you concurrently activate these 3 rows, these cells, I'm showing you only one cell in each row, but imagine that that row is 8 kilobytes or 16 kilobytes. You're doing this operation on 16 kilobytes at a time. If you concurrently activate these 3 rows, the cells get connected to the bit line with a reference voltage. And if at least 2 of these cells are charged, you get the charge state at the end. If at least 2 of these cells are discharged, you get the discharge state at the end. So basically, you get a bitwise majority function, which is at least 2, right? Okay. So that's your final state. And so you have a bitwise majority computation by concurrently activating 3 rows, which is computation. And we didn't add any majority logic, any gates whatsoever. We just have the capability to activate 3 rows. Now, clearly, majority you can decompose into AND and OR by setting C to 1 and 0. And in this paper, we proposed a way of doing NOT. NOT is actually easy, right? If you activate only 1 row, the complement of that row is on the other end of the sense amplifier because it's a cross-coupled inverter. And we propose a way of connecting this to over here, which is a bit disruptive to how things are routed in DRAM. Later works improve that. I'm not going to talk about that, but basically you can also have NOT. And once you have NOT and majority, or NOT and AND, NOT and OR, you actually have a functionally complete system. You can rethink all of your algorithms to operate in this bulk bitwise manner. And there are a bunch of algorithms that already operate a lot in a bulk bitwise manner, like bitmap indices. People have designed databases operating on large bit vectors. Microsoft had this web search engine, and there are a bunch of other things. And in this work, we've ported the bit weaving database to the simulator, where we could simulate these things, and we showed significant performance and energy improvements. So that was the MBit work over here. I think I will stop. Should I stop here, or what do you think?
It's fine, but
Okay, maybe I'll go a little bit more, because then the question becomes, how do you make this more programmable? I will go through some of these relatively quickly, because he's not intending to cover these, I think. So you can actually make this programmable in a general purpose manner. One way of doing this is changing your algorithm such that your algorithm takes advantage of these bulk bitwise operations directly. Another way is actually we want it to be less disruptive to the system. Can we actually incorporate some of these things in a sequential execution model? And the idea is relatively simple over here, but you need a framework to enable this. You can express any operation as hardware logic that looks like this. That's because hardware is and or not is functionally complete together. You can express convolutions, you can express matrix multiplication, FFT, whatever you want. And a person who wants an instruction expresses this way. We convert it into a majority inverter graphs, and we optimize that graph using electronic design automation tools that are developed for superconducting logic at EPFL, because they have actually a lot of majority gates in that superconducting logic. So we borrow their tools, we reduce the height of the graph, etc. And then we map this majority inverter graph to commands in DRAM, triple row activation, row clone, and we do some allocation of rows, etc. And we store a microprogram associated with that instruction in the memory. And the programmer or the compiler adds these bulk bitwise instructions in a sequential execution model. And when that bulk bitwise instruction gets executed, it basically gets sent to the memory controller. And the memory controller goes through this microprogram and executes the instruction inside DRAM. So this way you can incorporate any operation. You need to change the ISA or have a flexible ISA, but you are able to incorporate this operation. And we've shown in the SimDRAM paper that you can improve relatively small networks, let's say, significantly, but other operations also significantly. So you get significant performance and energy improvements. So that was SimDRAM. More recently, we built on this one because there are some other downsides of this very wide bulk bitwise execution. This is part of Geraldo's thesis. And the idea is, in many cases, you don't want to have a granularity of 8 kilobytes or 16 kilobytes, which is a row. Because in many applications, it's very hard to get that sort of, let's say, SIMD width. If you actually can reduce the granularity at which you can perform these operations, you can enable many more applications to be executed in DRAM. That's the idea. But to be able to do this, unfortunately, you need to change DRAM because there's no way you can execute. You can basically do chart sharing across a small fraction of the row today. But people have proposed ideas called fine-grained DRAM, which we were talking about earlier. If you can enable each mat to be operated individually. MAT is a smaller substructure inside a subarray. Essentially, a MAT is like 512 bits, and a single row has, a single subarray has many MATs connected to each other. By segmenting the word line, you can actually enable operation on individual MATs or subsets of MATs. So if you do that now, you can actually reduce the bit width that you're operating with to 512 bits, meaning that you can enable more applications that can be compiled into this. And in the subarrays where you're not operating, you can do other operations. This could be belonging to some other program, if you have that model, or the same program, but some other parts, other instructions. So you can actually have multiple instruction, multiple data model as opposed to single instruction, multiple data. So this is sector DRAM. This is a paper that I talked about from Ataberk that proposed a relatively less costly way of segmenting the word lines so that you can operate in a fine-grained way. In this work, we also added some reduction mechanisms, low-cost interconnects inside DRAM for reduction, because if you want to do computation inside DRAM, I think you need to add interconnects so that you can have communication. Existing memory chips are not designed for computation. They're designed for data delivery outside and data delivery from outside, right? If you want to do computation internally, some intermediate values, for example, you want to communicate internally. If you don't have interconnects, you have to go out, which means that you're actually increasing your data moment, or at least not reducing your data moment as much as you can. So I believe we need to rethink DRAM to be a lot more a lot more connected. And that requires the mindset of memory delivering data or memory consuming data to be, let's say, changed to memory actually doing computing on data. Okay, so this also eases programmability because our granularity in a mat is 512 bits. And this actually matches a lot of vectorized SMT widths like AVX. And a lot of compilers, including vectorizing compilers, can be retargeted to compile code into essentially the mat granularity. And that's what Geraldo did in his thesis. He added 3 LLVM-based passes targeting processing using DRAM execution. This is also open sourced online and completed transparently to the programmer. The compiler identifies code that could be auto-vectorized. Of course, the programmer can help this step. And compiler does code scheduling and data mapping and code generation for DRAM. So we have a mechanism to do that. And we simulate it and we get significant. These are workloads that are actually good workloads for this purpose. That's why you get these huge results, meaning they're auto-vectorizable nicely. Not all workloads are auto-vectorizable nicely, but we wanted to first target those workloads where we could actually do things. And if you actually look at these workloads, you get significantly higher energy efficiency compared to CPUs and GPUs. And the main reason is, first, you don't move the data out. Data moment reduces significantly. And you exploit essentially the whole parallelism inside the DRAM chip. So we're assuming inside the DRAM module, actually, not just one chip. So we're assuming for these results that these workloads can be parallelized across the entire DRAM module. If you think about it, almost every cell is working inside the DRAM chip to do computation. Okay, more recently, Geraldo, this is part of Geraldo's thesis also, we've shown that once you're doing this sort of bulk bitwise processing, different types of arithmetic representations can be better if you, for different types of bit width. And this work actually provides a library to choose your data representation together with your bit precision so that you can actually do better. For example, if your bit width is low, you can do much better with redundant binary representation, and you can do much faster multiplication that way, as opposed to bit serial multiplication. So I think there's more work to be done in this area. We have not really examined what kind of, how should you represent data so that you can enable computation to be much faster in this bulk bitwise manner. This is really scratching the surface, in my opinion. There's more to do in this area because people have developed a lot of data representation methods over decades, and they don't work well with bit serial processing mechanisms, a lot of them. Okay, so I'm going to stop here, but I will say that Ismail is going to talk about the fact that existing DRAM chips are already quite capable. This is something that we have figured out in our work in starting with true random number generation. We show that by violating the timing parameters to DRAM, you will find out that some cells fail randomly, some cells don't fail randomly. And you could use those randomly failing cells as a signal for as essentially random number generated cells. Are you going to talk about that? Okay, so in the Remulator and DRAM vendor workshop, Ataberk talked about that because he developed some mechanisms. But you can essentially do all of the operations that I described by violating the timing parameters. The thing to consider is that DRAM chips are not designed for this purpose. No manufacturer talks about this. In fact, some of the results that Ismail is going to present, manufacturers were surprised to see, and they came to us saying, can we actually make this happen together? Right? So it's good that there's some discovery that's happening that manufacturers are not even thinking about, and they're not thinking about because their goal is to design memory, not a compute engine, right? So if DRAM chips can do things, even without them being designed for doing those things, imagine what we can do if we can actually go and design that chip to actually do computation in a robust way. So if we change the mindset and do that, I believe we can do a whole lot more. Okay. Any questions before I give the floor to Ismail? Yes, please.
Okay, so big picture.
Sure.
I'm recently doing a lot with heterogeneous scheme,
Sure.
and it's actually not going that well. All of that we need to do is killing everything, and also on the top layers, compilation at least on like those middle layers and so on. So it looks to me like if you have a DRAM chip that is capable of pretty much doing everything, you would really need to have an entire system based only on this DRAM chip to work. How do you see it?
Yeah, I'm not sure about the only because I think you will definitely need to have ways of exploiting the DRAM chip to use its good characteristics. But you could also potentially partition the computation. Like, of course, it depends on what you're trying to do, and I don't know exactly what that is. But if you can partition the computation between compute-centric and memory-centric parts and minimize the communication across those, I think you can take advantage of both capabilities of the DRAM chip as well as something else. But what we tried to do in the previous works is to have only execution in the DRAM chip. So I agree with that. It's good to start with that. But over time, heterogeneity can help.
I don't see it right now.
Okay, yeah. I think we're still early in like PIM development, right? And what kind of PIM system are you working with?
Working with AppMem.
Okay.
I used to work with AppMem on also like proprietary.
Okay, sure. Yeah, AppMem has a lot of limitations, as we may discuss later on. So yeah, okay.
In their chips and
Mm.
very actually people who adapted what the industry
For which one? For SK Hynix's chips or? Mm.
if you do other memory chips, this kind is one.
Mm.
There are other.
Yeah, yeah. Mm. Mm. Mm.
What do you see as what needs for industry to adapt?
Yeah, yeah. Mm-hmm. Yeah, adoption. I have a section on adoption, but I didn't talk about that. Yeah, I think the adoption is really a programming mechanism. So if you can actually easily offload your computation without doing anything, that's the easiest thing to adopt, and you get significant performance and energy improvements, right? That's what the industry really wants. I think we're not there completely yet, but I think there is a lot more that has happened in the last few years that can enable that. So in the end, I would say the biggest thing is programming, compilation, runtime system to offload. Yeah. Mm. A lot model where, sorry? Yeah, I think so. I would say we want to not program these PIM systems as much as possible. But if someone is willing to program, they can get a lot more performance out of it. So for example, if someone can take advantage of the results Ismail is going to present and do that in real systems, I believe they can be ahead of the game. But it's difficult to do. That's the, yeah. So it requires some courage to do something different, let's say. Okay.
Yeah.
There's one in the front over here.
Thank you. So I guess when I was watching this, I had like this feeling that there's general, like right now we're very general purpose, the processor, memory is just memory, etc. And then with processing, using memory and processing new memory, getting more specific, and you talked about even treating it like an accelerator, somewhat. At what point do you think we begin to lose the general nature of memory? And I think at that point also, like, that's when like maybe the cost becomes too much.
Yeah. Yeah, that's a great question. Basically, I mean, it depends on what you add to the memory side, right? That's why 3D stacking is nice, because there's already a logic layer that you have, and you can potentially customize it for your purpose. But you can also treat this thing as memory, right? So if you're adding next to each bank a huge processor like UpMem did, that is very costly, no question about that. And you lose a lot of memory capacity to that logic. If you're, for example, doing the computation types by activating DRAM rows, that's actually not that costly. You're not adding that much logic. You're not losing that much capacity. So in the end, the trade-off is how much capacity are you losing, which is really what we want for memory, right? Capacity, latency, etc. In most of these cases, you're not losing that much latency, but you may be losing capacity versus how much computation you're adding. So if you're in a lot of these works, I think you can enable memory to be memory while also being a computation device, unless you actually added huge amount of computation that removed a lot of memory from your system. That's why I think having planar two-dimensional DRAM and adding logic to it is very expensive. Of course, depends on what you add, but it's very expensive. If you have 3D stacked memory, you have a lot more room to play with.
Thank you.
Okay.
Any other questions? Thanks a lot.
Okay, thank you. Yeah. No.
Okay. Oops. This was the last slide. Sorry. Yeah. Hello, everyone. Today, I'm going to talk about understanding the computational capabilities of real DRAM chips and the robustness issues they introduce. So I'm Ismail again, and I'm interested in processing in memory, as you can tell. And so in this talk, I'll be focusing on these three works, mostly in the first one, and I'll mention the capabilities of the second one, and I'll add a warning for processing using DRAM for the last one. So let's start with the first one, functionally complete Boolean logic in real DRAM chips, experimental characterization and analysis. This was published in HBC 2024. So our motivation is, as Onur discussed, processing using DRAM can alleviate the performance and energy bottlenecks caused by the frequent data movement between main memory and computing units. And prior works show that existing DRAM chips can perform 3-input majority and 2-input AND and OR operation by violating timing parameters, basically realizing what Mbit showed. However, the problem is this proof of concept demonstrations on real DRAM chips do not provide a functionally complete operations. They only have AND and OR operations or data copy. And they do not provide any NOT operation. And the AND and OR operation are just limited to 2 inputs. So in this study, we conduct an experiment on 256 DDR4 chips from 2 major manufacturers. And we observed that actually off-the-shelf DRAM chips can perform NOT operation and 2, 4, 8, and 16 input AND, NAND, OR, and NOR operation with a relatively high reliability. And the environmental effects and operational parameters such as data pattern and temperature only slightly affect these reliability of these operations. So let me give you a quick recap on DRAM organizations. So this is a DRAM module, consists of many DRAM chips. And inside the DRAM chips, we have multiple DRAM banks. Within each DRAM bank, we have many subarrays, and within each subs, we have sense amplifiers. So if we take a closer look to some part of the DRAM bank, so a subarray consists of 2-dimensional array of DRAM cells, a row of DRAM cells called DRAM row, and they are connected through word line, and a column of DRAM cells connected to sense amplifiers via bit line. So there is a new architecture in DRAM. I think it's employed in starting from DDR4 to achieve high density DRAM chips. They employ open bitline architecture. So in this architecture, each subarray's bitline is connected to 2 rows of sense amplifiers, one above and one below. And this resulting in neighboring subarrays to share a common sense amplifier. And during an activation, another bitline in a neighboring subarray is also involved to serve as a reference of the sense amplifier, which is the bitline bar in this example. And after a successful activation, the bitline and bitline bar have a complementary voltage. This is because a sense amplifier consists of 2 back-to-back inverters. So we're going to leverage this to realize NOT operation in real DRAM chips. And there are 3 major DRAM operations that we focus on in this study. The first one is activate, which fetch the raw content in the sense amplifiers. The second one is read and write, where you read and write your data. And the third one is precharge, which precharges the bank for a new activation. In this study, we experimentally demonstrate that off-the-shelf DRAM chips can simultaneously activate up to 48 rows in 2 neighboring subarrays, can perform NOT operation with up to 32 output operands, and can perform up to 16 input AND, NAND, or AND NOR operations. So in order to test real DRAM chips, we have a DRAM testing structure developed from DRAM Bender, which enables us to have a fine-grained control over DRAM commands, timings, and temperatures. And this is our laboratory to test many DRAM chips in parallel. And in this study, we test a total of 256 DDR4 chips from 2 major manufacturers, SK Hynix and Samsung. And we cover different die revisions and chip densities. Essentially, you can think of some slight changes to DRAM microarchitecture. So let's start with the first one, the capability of activating multiple rows in neighboring subarrays. So the key observation is really the violating timing parameters to activate multiple rows. So here we have an example of 2 subarrays, neighboring subarrays, which they share a sense amplifier, subarray X and subarray Y. And let's say that in subarray X, we have row A, and in subarray Y, we have row B. So this is how we activate by respecting the timing parameter in DRAM. You activate row A, you wait for some time, which is TRAS, 36 nanoseconds, and then you issue precharge to close the row A to prepare the bank for a new activate, and then you activate row B. Again, if it means precharge and activate, you wait for some time. In this study, we observed that if you violate these timings greatly, from 36 nanoseconds to 3 nanoseconds, 14 nanoseconds to 1.5 nanoseconds, you activate many rows at the same time. This is because DRAM actually employs a hierarchical row decoder circuitry. Whenever you open a row, you actually assert multiple signals in the tree. You can think of as a tree, and you open multiple, let's say, assert multiple signals in the tree. So when you don't give a DRAM enough time to assert those signals, and you activate even more, which is the row B in this example, you activate many more intermediate signals, and as a result, those signals result in activating multiple rows, more than 2. And in this study, we observed that you can activate up to 48 rows in 2 neighboring subarrays. And let's see how we leverage this to perform NOT operation. So here we have 2 subarrays. So SRC, source row, is in the 1 subarray, top subarray, and the ST destination is in the lower subarray. They are neighboring subarrays, and as you can see, they're sharing a sense amplifier. And as I said, sense amplifier consists of 2 back-to-back NOT gates. So the key idea is really connect rows in neighboring subarrays through a NOT gate by simultaneously activating them. So what you will do in theory is that you will activate the source, which will share its charge. And then the bit line that source connect to will have A, and the bit line bar, which destination connect to, will have negated A. And then if you activate destination without deactivating, like precharging the bit line or the sense amplifier, you will be getting a negated A, not A, in the destination. So let's see how we realize this in real DRAM chips. So again, we have source and destination. They're neighboring subarrays, and initially they are at the ground, 0, logic 0 value. And the bit lines are precharged to VDD over 2. So we first activate source, which will connect the source to bit line. And then we will wait nominal timing parameters, which will share its charge, which will drive the bit line to ground, and which will drive the bit line bar, destination's bit line, to VDD. And then we issue pre-charge and activation destination back to back. So what will happen is, if you violate this timing, it will, because of the activation to destination, you will connect the destination to bit line. But since you violate the timing over there, you don't give enough time DRAM to pre-charge the circuitry, right? So sense amplifier is still enabled. The bitline bar, the destination's bitline is still VDD. And then you wait for some time again, as if you activate the destination. It's like charge restoration. Now the negated value of the source is written to destination. As a result, now you have the NOT operation in real DRAM chips. In order to assess the reliability of these operations, we define a metric called success rate for a DRAM cell, which is the percentage of trials where the correct output of a tested operation is stored in the cell. So here, for example, for the NOT operation, for this specific cell, as you can see, 2 of them is correct, 2 of them is incorrect. So the success rate for this specific cell is 50%. So we test 10,000 trials for, I guess, more than 4 million of DRAM cells across many modules. So the key takeaways from this NOT operation is off-the-shelf DRAM chips can perform this up to 32 destination rows, and temperature has a small effect on the reliability of these rows. So here, let's look at the results. In the x-axis, you see destination rows. And the y-axis, you see the success rate. So one number of destination row, if it's 1, that means that you will have just one destination. You will be negating the value of the source to just one cell. But if it's 32, you will be simultaneously negating the value at the 32 cells. So as you can see here, there is at least one DRAM cell, actually many more DRAM cells, that can perform an operation with a 100% success rate. And we conclude that you can actually perform this NOT operation in real DRAM chips, hopefully most of the cells reliably. And now let's take a look at the third technique, how we can perform 16-input AND, NAND, or AND NOR operations. So the key idea is really to manipulate the bit line voltage by activating multiple rows at the same time. So here we have an example of, again, neighboring subarrays. In the top subarray, we have A and B. In the bottom subarray, we have X and Y. So when you pre-charge this, they have a reference voltage, which is VDD over 2, right? So if you activate multiple rows at the same time, assuming we are activating 4 of them at the same time, now on the top of the bit line, you will have the function of A and B, which is actually the average function. So in the top bit line, you will have the average voltage of A and B. In the bottom bit line, you will have the average voltage of X and Y. And then sense amplifier, after the successful activation, sense amplifier will compare the results, and it will try to understand which one is higher voltage, which one has lower voltage. So let me show you how the basic intuition to perform 2 inputs and then NAND operation. Again, we have 4 cells. In the top of subarray is reference subarray, and the bottom subarray we have compute subarray. And in the reference subarray, we have VDD and VDD over 2. And in real DRAM chips, thanks to a prior work, we can actually store VDD over 2 in a cell. And in the compute subarray, we will have X and Y. And then assume that this activate, pre-charge, and activate our key command sequence will activate 4 of them at the same time. So as I mentioned, when you activate multiple of them, the function is average. So when we perform the multiple row activation, reference subarray will have the average voltage of VDD and VDD over 2. And the bottom subarray will have the average voltage of X and Y. So let's go through the truth table quickly. So the first row is where X and Y both 0. So the average of VDD and VDD over 2 is 3 VDD over 4, and the average of 0 and 0 is 0. Since the reference subarray has higher voltage level, sense amplifier will compare the voltages, and now reference subarray has 1, compute subarray will have 0. And when the inputs change, so X becomes 0, Y becomes 1, it's still lower than the reference subarray's voltage. And as a result, you will get, again, 0 in the compute subarray, 1 in the reference subarray. And the 1, 0 is the same case. We will get 0 in the compute subarray and the 1 in the reference subarray. And for the last one, where we have both VDD and X and Y, now the compute subarray has higher voltage value than the reference subarray, right? So as a result of this, compute subarray will have 1 and the reference subarray will have 0. If you take a closer look to this truth table, now the compute subarray is actually a function of AND operation of X and Y, while the reference subarray is a function of NAND operation of X and Y. So this is the key technique that we're proposing here. So if you carefully initialize the reference subarray, you can actually realize also an OR and NOR operations as well. So you can take a look at the paper for more details about that. So for these operations, we observe that off-the-shelf DRAM chips can perform 2, 4, 8, and 16 input AND NAND OR and NOR operations. And they can perform this with a relatively high reliability. And the data pattern slightly affects the reliability of these operations. So let me show you an example result. In the x-axis, we will have the number of input operands, 2 input, 4, 8, and 16. And the y-axis, we have the success rate. And the hue, the colors will show the operations type. So as you can see here, in every number of input operands, we can actually, again, perform AND, NAND, OR and NOR operations in some cells with 100% success rate. And if you take a closer look to 16 input AND, NAND, OR and NOR operations, the average success rate is more than 94%. And for more details and for more results, please check our paper on the archive. And this FCDRAM, a functional complete Boolean logic in real DRAM, is actually open source, and you can directly test if you have the FPGA and the infrastructure. And this was FCDRAM. Do you have any questions, or I can continue? All right. Let's move to the second one, which is simultaneous many row activation in off-the-shelf DRAM chips. So in this study, we showed that actually if you activate 32 rows at the same subarray, you will be getting not just majority of 3, but you will be getting majority of 5, 7, 9, and so on. And with this 32 row activation, you can actually replicate the input. So in the majority of 3, what we had is ABC, right? So majority 3, ABC. But if we have more rows, 30 rows, for example, you can replicate 10 of A, 10 of B, 10 of C, which will be increasing the bitline deviation, and it will give you a higher robustness, higher reliability of majority operation. And we observe that you can actually increase the average success rate more than 30% with this input replication technique. And we also show that you can copy one row's content to multiple other rows at the same time. So let me give you a quick idea on how we perform multi-row copy, which is very straightforward. So the key idea is really you simultaneously activate many rows to copy one row's content to multiple rows. To recall row clone, we had source and destination, right? What we do is that we open source, which will fetch the contents to sense amplifier, and then you open the destination, which will write back the row buffer's value to destination row. In the multi-row copy, things are, now we have many more destination rows, up to 31 other rows. What we do is that after activating source, we will be activating this 31 other destination rows at the same time, and we will be getting multi-row copy up to 31 other destination rows concurrently. And this operation is actually very robust. We observe that across all tested number of destination rows, the average of success rate is more than 99.98%. And we conclude that off-the-shelf DRAM chips can actually copy one row's content up to 31 other rows with a very high success rate. And for more details and many more results, you can also check this paper. And our Simra DRAM work, this work is actually open source and artifact evaluated, and you can find it and test it right away from this link. And the slides are already online on the website. So that's what's a very quick recap of this work. And I'll be directly going to the next work, PATHAMMER, where we observe the read disturbance effects of processing using DRAM in real DRAM chips. So the motivation is processing using DRAM is very promising to elevate data moment bottlenecks. But in order to perform these operations, we need to perform multiple row activation. However, modern DRAM is subject to read disturbance, right? If you activate just one row repeatedly, you will be getting bit flips in nearby rows. And in processing using DRAM, we will be actually activating multiple rows at the same time. So in this study, the problem is no prior work studies the read disturbance effects of multiple row activation. And our goal is then understand and analyze whether there's an read disturbance effects of multiple row activation. So in this study, we test 316 DDR4 chips from 4 major manufacturers to understand the read disturbance effects of multiple row activation, which we call pot hammer. And we observe that pot hammer significantly exacerbates the read disturbance. So the minimum hammer count to induce the bit flips now reduced by more than 158 times. And it can bypass the DRAM row hammer mitigation. It's already employed in DDR4, and it induces more than 10,000 times more bit flips than normal row hammer attack. And we try to adapt latest industry solution to row hammer per row activation counting for pot hammer. But unfortunately, the effects are so severe and adapted PRAC solution incurs almost 50% of an performance overhead. So let me give you one result of this work. So you remember that simultaneous multiple row activation where we violate timings and get multiple row activation, right? So, and hopefully you remember read disturbance in DRAM where we just activate one row all the time. So what we do is that in this study, again, we test many more DDR4 chips. So what we do is that now instead of repeatedly activating one row at a time, now we are activating multiple rows at the same time to perform majority operations in DRAM operations. Now we are exploring here, analyzing here that if we sandwich a row, which is not a compute row, what will happen? So in the x-axis, we have the number of simultaneous activated rows. One means row hammer, the other means the multiple row activation, processing using DRAM operations. And the y-axis shows the minimum hammer count to induce the first bit flip. And as you can see, for row hammer, the lowest we observed was 4,000. You need to perform at least 4,000 activation to induce the first bit flip. But with processing using DRAM operations, you only need as low as 26 operations, which is 159 times lower than row hammer. And actually, this is consistent across all tests of number of simultaneously activated rows. As long as you sandwich a victim row, now you're exacerbating the read disturbance a lot. So in the paper, we discuss how you can modify your DRAM chips, how you can adapt, and what are the other effects like data pattern, access pattern, the row clone operation, etc. So you can find them on the archive. And that was pot hammer. So that concludes my talk, and I'll be happy to answer your questions if you have any. Yes.
Nice. Yeah. So I was wondering, like, so if you I think processing using memory kind of introduces like read disturbances. I was wondering, do you have any insight also like if the aging of the DRAM is also kind of increasing if you use this type of techniques?
So that's really a good research direction, understanding how aging affects read disturbance. For now, in the literature, unfortunately, there is no robust aging methodology to understand whether DRAM is aged or not, or accelerated aging as if like in other memory technologies. So unfortunately, we don't have enough information about that.
So first we need to actually introduce how.
Yes, yes, and then we can understand the effects of it. Yeah, yeah. Yeah.
Class and at a higher level, since there is some failure rate.
Mhm.
Up here. It's like success rate. Maybe not success.
So it's really success. It's really the underlying circuit level thing. So in this second paper, what we did is that we're trying to replicate it to increase the robustness of this operation. So you have a lot of noise when you activate multiple rows. In the end, this is a real DRAM chip that is not designed for this purpose, right? So because of the noise, the result can change. Sometimes you can have this bit flip, sometimes you don't. And if you increase the you replicate the inputs a lot of times, you can actually become more robust to noise and other things. So you might be increasing those things. But as you can say, for example, if most significant bit flips, the result will be catastrophic, right? So you can actually characterize your DRAM chip, understand which cells or which columns are, let's say, more robust than others, and you can try to map your data for that. But in the end, they might be still subject to errors.
So thank you. That's a good talk. So I just want to make sure that my understanding is correct. So when you use this processing memory using PIDRAM to do this, you have to, there's the cost of initializing the reference array, and then also you double the memory utilization of anything that you're doing operations on, right? Like if you do it not, you have a copy of the original data, and you also have the copy of the not. So this is like not in place. Okay. What do you think? Like our race, because like obviously this is in DRAM as it is today. Do you have any ideas on how you might be able to do things more in place, or reduce this cost?
So one of the issues is that DRAM activation is actually destructive. So if you don't wait, for example, activate the precharge to nominal time, you will be distracting that content. So if, for example, if you don't care, if it's an intermediate result that you don't care about, you can actually do in-place majority operations. There are some works that proposes that. We were trying to do it in a way that you will still keep the initial value, right? So because you might be getting some errors, you might want to do it again, etc. But if you would like to optimize the storage cost, yes, as you said, you need to do it in place, or after you do it, you will make it, I don't know, invalid or such. But in DRAM directly, in Mbit, there's already a direct in place NOT. You can do that. But for real DRAM chips, as we discussed, not designed for this. It's not directly possible to do in place NOT operation, unfortunately. But with some tweaks in real DRAM chips, such as there's a work from 2016, Lisa, HPCA, you can actually do those operations in place also.
Okay, thank you.
Thank you. Yeah. Okay, thanks a lot. Did you send your slides? This one. Take this. You want to introduce you?
No, it's fine. Do you want to introduce me?
I don't know. You want me to introduce you?
Introduce me then.
I don't have your bio. I have your bio actually.
It's okay. I can just go.
No, Nisa is going to introduce you.
Okay.
you can use this also.
Hmm.
And you can here if you want to if you can. Yes, please.
Okay, so the next talk is by Ataberk. Ataberk Olgun is a senior PhD student at ETH Zurich, working with Professor Onur Mutlu. His broad research interests include designing secure, high-performance, and energy-efficient DRAM architectures. Especially with the worsening Rowhammer vulnerability, it is increasingly difficult to design new DRAM architectures that satisfy all three characteristics. His current research focuses on deeply understanding and efficiently mitigating the Rowhammer vulnerability in modern systems.
Thank you for the quick introduction. I'll be talking about PIDRAM. It's an FPGA-based framework for end-to-end evaluation of processing and DRAM techniques. And we'll cover a bunch of the techniques that Professor Mutlu and Ismail talked about already. So we've seen a bunch of nice techniques that we can implement in our systems in real DRAM chips and maybe get some performance and energy benefits out of those. If you look at the compute stack, the classical view of the compute stack, this would mean somehow making changes across this across the layers in the stack to enable, let's say, an example bulk data initialization application using the primitives provided to us in the DRAM chips, such as the row clone operations, where we copy data in row granularity inside a subarray. What sort of changes this requires is basically if you go layer by layer, you need some sort of support for custom timing parameters closer to the logic and microarchitecture layers. You need to implement some sort of control logic for controlling processing and memory operations. You have to expose these operations to the software for the programmer to be able to execute and get any sort of benefits out of them. And you need some supervisor software that provides basic system support, like virtual memory and memory allocation for bulk data copy operations. PIDRAM's goal is to bridge this, what we call the system gap, with customizable hardware and software components so that its users can rapidly implement new processing and memory techniques. They can solve system integration challenges involved in implementing these techniques, and also analyze and evaluate these end to end. So I'll skip some of the background here and try to keep this short so we can all go to the coffee break on time. I don't think we need this background. These are just classic DRAM backgrounds that we have already seen in previous talks. But I'll just want you to recall some of these processing and memory operations, such as the row copy operation, which allows us to copy data, bulk data and row granularity inside a subarray, and also true random number generation. There are many more techniques that you can implement, but we will cover these two, the first two, in this as part of this work. So the key idea of row clone is to basically copy a source row. This is the orange row in this picture, to the destination row, and we do that through the sense amplifiers. So there you can do this in two steps. First, you bring the source row to your sense amplifiers or the row buffer, and then you have to take the data back to the destination row. If you look at today's DRAM chips, the first operation is already basically supported. That's an activate command. And to implement the second one, we will rely on carefully crafted DRAM command sequences that Ismail described. So if you send an activate precharge activate command sequence with greatly reduced timing parameters, you can copy a DRAM row instead of opening two rows sequentially. But this was already covered. I'm not going to dwell on it for so long. As for true random number generation, what we in this work leverage is DRAM latency variation. So I'll try to describe you what's going on here. We have a bunch of DRAM cells in a subarray, and the size and the color of the cells indicate how prone they are to failures when we access them with a reduced read latency. So we activate the row and we violate the read timing parameters. We read much earlier than what the DRAM is designed for us to read. And if a cell fails, most of the time, that's a small and a red cell. If it fails, not frequently, not so frequently. That's like a larger green cell. The key observation here is there are some cells that fail with a 50% probability, very convenient for us to use them to generate random numbers. And that's precisely the key idea of D-range. That is to say, if you just violate some of the DRAM timing parameters, you can generate two random numbers in today's DRAM chips. And that's what we do in this work. So these are the slides I've covered about system support and PIDRAM's goal. I'll briefly talk about how PIDRAM satisfies these goals. So it is a flexible framework that is useful for studies on commodity DRAM-based processing and memory techniques, such as the ones we described over the previous slides. And it has four key components. First, on the hardware side, we have a processing and memory operations controller. Another component to provide support for custom timing parameters that we need to violate DRAM commands timings. On the software side, we have an interface, PIM operations, processing and memory operations library for application developers to use, and also some custom supervisor software that provides the basic support for primitives like memory allocation for row clone operations. We attach these components to a real system design. These are the components that I've talked about in the previous slide to form PIDRAM's whole system. And we have Rocket chip, which includes a small RISC-V CPU core. And we also have a DRAM module that we interface with to perform these processing and memory operations. I'll describe these one by one, and then I'll show you the case studies that we did using PIDRAM. So the first one is the processing and memory operations controller. It decodes and executes PIDRAM instructions, such as in DRAM copy operations. It is connected to the hardware system as a memory mapped module. So meaning that it receives the PIDRAM instructions over the memory bus from the RISC-V core. And there are three registers that the programmer will set the values of and to use them to initiate these processing and memory operations. The second component is the PIDRAM memory controller. This is a specialized memory controller that provides support for violated timing or command sequences that already come with violated timing parameters. So you can perform these row copy operations in this example in real DRAM chips. We also implement ways for the developers of PIDRAM to basically use and easily replicate our state machines and add new command sequences with violated timing parameters. So if you look at PIDRAM's baseline design, it should be very easy for you to add a new command sequence to perform bulk bitwise operations instead of just row clone operations. And the physical interface that you see here, it just controls the DDR3 interface in this example. It receives commands from our specialized command scheduler, and it sends these signals over the DDR3 interface to basically control the DRAM device. On the software side, we have the PIM operations library, or PIM-olib. This exposes the PIM functionality to the software stack. So to perform a PIM operation, a typical function here will use load and store requests to communicate with the PIM operations controller over the CPU core. And the last component is the custom supervisor software. It exposes these PIM operations to user applications via system calls. We implement some of the necessary OS operating system primitives to develop end-to-end techniques, such as the one I kept talking about is memory allocation and management for in-DRAM copy or row clone operations. And we will talk about that in a little bit more detail later. I'll skip this execution flow. I think it's a bit mechanical and we don't have so much time, but we will share the slides. So if you're interested in this, I think it's a good walkthrough through the internals of PIDRAM to show you how an operation gets executed. So we have four key components that orchestrate PIM operation execution in PIDRAM. And we have this PIDRAM full system design implemented in this FPGA board. This is the full prototype for PIDRAM that's readily available today. You can download and use it and perform processing and memory operations with great success. So it has a simple RISC-V core, as I mentioned, and it has this, what we call a processing and memory enabled modules, DRAM modules, that you can see the details of here. So I'll continue with the case studies we performed using this prototype. Just recall that for row clone, we basically violate the DRAM timing parameters and execute a sequence of activate, precharge, activate commands. To implement this in PIDRAM's baseline system design, we have to extend the memory controller to support this command sequence with violated timings. And we also expose the operation to PIM-lib by implementing the copy instruction. And this only takes 200 lines of Verilog code, which you can use to quantify the amount of effort involved in extending this infrastructure. I believe this is a small number, but I will be happy to take questions. Okay, so there are two important challenges in integrating row clone into a real system, and we explore them here. The first one is memory allocation for row clone operations, because you can only copy data that's inside main memory and inside a single subarray. So you cannot copy data from one subarray to another subarray. The locality of the operations are relatively limited per se. The second challenge is maintaining coherency, because the data we're operating on needs to be in DRAM. So if you're copying a source data to the destination data, destination source row to destination row, that source row should have the most up-to-date copies of the data in your cache hierarchy. To solve the second challenge, we basically just implement a CL flush instruction in the RISC-V CPU. When we were working on this prototype, the CPU design did not come with any CL flush instructions. That's why I'm mentioning it here. It was kind of like a contribution to the rocket chip source we were using. And what we do is basically, before performing any row clone operation, we must cache line flush every single cache line that this row is mapped to. As for memory allocation, I'll describe this problem in more detail. So we have in this diagram 2 banks and 2 subarrays and a bunch of combinations of memory allocations for source and target operands that either fail or succeed for row clones. So the first one fails because we couldn't fill up the whole row, source row and the target row, with valid data per se. So if we do this operation, we will overwrite this part of the destination row with some data that we don't know. We don't want to do that. The second one shows you another unsuccessful mapping. For you to copy data from one, let's say, bit of a source operand to another bit in the same index of another destination operand, they have to reside on the same bit lines. You cannot copy data across bit lines, and this allocation kind of suggests that you want to do that, which is not possible. The third one is simple. You cannot copy data across banks or across subarrays. And the fourth one shows you a successful allocation, basically, yeah, a successful memory allocation that can perform row clone operations. We design a memory allocation function that basically ensures we get the fourth mapping. And I won't go into the details of that in the interest of time, but I'll invite you to read the paper for details. We evaluate this system using a bunch of micro benchmarks that do either copy operations using the CPU, which is load and store instructions, or row clone copy operations using the DRAM chip. And we evaluate this with and without CL flush, meaning that in one case, we will assume that data is up to date in DRAM, so we don't have to do any CL flush. In another case, we have to evict everything. We also evaluated real workloads, just one actually. That's the libquantums from Spec 2006 benchmark suite. This was very difficult, but we have promising results. And we also ran a bunch of copy and initialization heavy workloads, but these are more micro benchmarks than end-to-end workloads. So just to summarize, we have a relatively large throughput improvement provided by row clone copy and initialize operations in the range of, well, 89 to 120 times almost. And the reason why this number is so large, I'll mention that is our CPU baseline is a bit too wimpy. It's a 50 megahertz in order core, so it cannot really extract all the bandwidth that's available. And this is one limitation of this framework in its current state. If you involve CL flash operations into this, then your benefits reduce significantly. And the key takeaway here is that perhaps we have to find different ways to deal with the coherency problem than using CL flash operations. But there are prior work in this area that I could refer you to if you're interested. Now, for other workloads, I'll just summarize. For a fork bench, basically, it's fork is a system call that you use to generate copies per se of your workload. And if your workload already occupies a lot of memory, this shows you that using row clone to copy your workload, your performance benefits increase with the amount of memory that it already occupied, which makes sense. For compile, which is an initialization heavy workload, we see 9% execution time reduction, which is reasonable given that the workload evaluated only spends 17% of its time on initialization. And for the end-to-end lib quantum workload, we see 1.3% execution time reduction when we replace CL log calls or call log calls, which initializes, allocates and initializes memory we replace that with bulk data initialization operations in DRAM, and we get 1.3% execution time reduction. So I'll be skipping this. Maybe I'll just mention that we also, as I described this earlier, so we implemented this derange mechanism where we find cells that fail with 50% probability when we access them with a reduced latency. And the idea is you identify a bunch of those in a cache line, and then you repeatedly access this cache line with reduced timing parameters. And we show that you can generate true random numbers at a relatively high throughput using our prototype, using this technique. So that will be all from my side. I'll skip the executive summary in the interest of time and take questions instead if you have any. Oh, there's one question. Meanwhile, I'll just reiterate that this is completely open source, and if you have the FPGA board, you can download it and start running things on the FPGA board. It's real.
Great, thanks.
Yeah.
Just interested in knowing how like to identify those cells that fail with probability 50%, because like even like a very slight bias in this like probability would lead to catastrophic like failures. This running generation in any like security critical domain. So is there any reliable way to identify those cells? And is it really that they fail with 50% probability? Or...
Yeah. So for our, as far as our experiments go, we find them to be stable. Like if we identify a cell to be 50% probability, it is 50% probability, even with some small temperature variations. Temperature has a huge effect, by the way. Like if you test at a different rate, like if you test at 80 degrees Celsius, your 50% probability of failure cell will change. Yeah. But if you wanted to have a full implementation, I think you would, no matter what, you would have to implement all these health checks that go along with any true random number generator that we have in our systems today to check for the source of entropy, the quality of the source of entropy, right? Like if something like what you said happened, you would either stop generating true random numbers, or you would maybe change your entropy source to some other cells. There are many of these cells, and the derange paper itself that I can refer you to will has covered a much like vaster space in terms of characterization, like voltage, temperature effect, etc.
Thanks. So just one clarification.
Yeah.
So, like you said, so like your analysis generally concluded that you can rely on those cells, like at least in normal system, like conditions. Okay.
Yeah. Yeah. You can.
This is actually local and huge.
Yes.
So there are a lot more techniques, not just PIDRAM, local pure, for example, waste reduction. It's not just to do random number generation, but some other operations. Here are the two compare actually two rows
Yep.
in different subarrays to refresh. So would it be easy to extend this to support those?
Yeah, pretty much. So the main problem for those is for the hardware side, you would need to add a new state machine or like extend the state machine we have in the memory controller with new logic, but you can largely copy what we have for row clone because the underlying primitive is the same. You violate the timing parameters by to a different extent for each different operation that you want to support. The difficult part would be the mapping, data mapping, and all these software level issues that you would need to deal with. So what we have implemented on the software side is really for specialized to bulk data copy operations, but you have to tune it to work for bulk data, bulk bitwise operations, and that's more involved than what we have. So yeah.
Thanks.
Thanks.
So we do the coffee break now, and we will be back at 4 p.m. with the professor. Oh, thanks.
Find a better slide.
I figured out some very seat guy. Yeah. That was right on. I was fighting the battle of increase check. I'm leading. Yeah. Then it was part of my vacation up in Conference Place. Hear you guys talk. Like Safari group. Like, say hi. Hi. Yeah. Really? Nice to meet you. Yeah. Yeah, a lot of different topic. Yeah. Yeah, I just like, because my background is in security, like offensive security work. I work for like other contractors right now. Like excited, but it's like my background's like systems type stuff, computer science side of things. So getting more into the architecture side, understanding what's actually happening. It's kind of one of my goals. Yeah. Probably broadens a little bit, especially like one of the reasons I applied for masters instead of like applying places. I felt like I had too many interests at the moment, and I need to like squeeze a little bit, squeeze down a little bit to something more, personal in that sense. Yeah. So undecided. I also feel like if I wanted to keep doing a lot of security work, I might,
I already get to do really cool security work for my job, and I get paid a lot of money for it. So, it makes less sense to pursue like graduate education if that's what I want to do. So, think broad. Perhaps. Probably. I'm with you. It's, I think honestly, I didn't quite expect that. And then, it's one thing with a lot. And now, I've been here. Like housing. People in the US are playing about it. Well, that's fine. I was looking at wow, people in the US are complaining about housing. They didn't get over that. It's not. Waiting on. Not too. No, they're not. I want to pull it out. It's like, you can see them now. Where's the hotel? You don't want the hotel. Yes, I do. So it's like 24.5 hours hour. So I go down Sunday night. Sorry, class would be back for so like I was like I debated it out. Yeah, I was like, well, yeah, I was like, I don't want. I'm like,
Okay. Okay. All right. So we're gonna start the second session with Professor Gibbons. So Dr. Gibbons is a professor in the computer science department and the electrical and computer engineering department at CMU. He received his PhD in computer science from the University of California at Berkeley. Prior to joining CMU, Gibbons was a researcher at Bell Laboratories and Intel Research Pittsburgh and co-director of the Intel Science and Technology Center for Cloud Computing. His research areas include parallel computing, databases, machine learning systems, computer architecture, and distributed systems. Recent projects range from the theory and practice of processing in memory. For example, the best runner-up at VLBB 2023, computer architecture support for robotics. For example, the best paper at Sigmatrix 24, and his 200 plus publications span theory and systems and have been cited more than 46,000 times and with an H index of 87. Gibbons won the ACM Paris Canalakis theory and practice award for pioneering the foundations of streaming data analytics. He was founding editor-in-chief for the ACM Transactional Parallel Computing, associate editor for the Journal of the ACM and other journals, and program area general chair for over 1,000 conferences. Gibbons is both an ACM and IEEE fellow. Please feel free to start.
Okay, so the lesson is send us shorter bio if you want to. I wasn't expecting the complete bio to be read, but okay. So today I want to talk to you about this work we've been doing for several years now on looking at applications that arise in the context of databases and how they can run effectively on processing memory. Key takeaways of the talk. Processing in memory is a unique way of doing computation because it combines the aspects of distributed memory computation, which is what goes on at the PIM modules, with the shared memory computation that goes on at the host front end. And you really want to take advantage of both these two pieces, right? And that makes it interesting computationally. It raises sort of new challenges that haven't arose in other contexts. One of the things that makes it interesting is that the asymmetry between the host processor and the PIMs, okay? And in particular, we're going to be focusing a lot on sort of UpMem style platforms where, you know, they just took some of the DRAM DIMMs and replaced them with these processing equipped ones and put simple in-order cores. And the result of that is that the sort of aggregated bandwidth in and out of the host front end matches, right? It can sort of absorb the work that the PIMs can do and back and forth. And so it's really, when you think about the uniqueness of this style of computation, at least the kinds of work that we've done, it really relies on this asymmetrically high special node, right? That has much more bandwidth, much more compute power. And we'll get into that towards the end of my talk. If you just focus on the distributed memory part of it, the part that the PIMs are doing, where they're all working on their local memories, then you have the classic challenges that arise in distributed memory, okay? And that is, if you're pushing compute to data, then if the data that all the tasks want happens to be concentrated on, for instance, one PIM module, then you get no parallelism whatsoever, right? And so the whole thing falls to its knees. And so, and on the other hand, if you think about classical ways we do load balancing, they all involve migrating data around to accommodate load, and that's data movement, and that's the whole reason the whole thing we're trying to avoid by going to PIM. Okay, so we're going to talk about this sort of Venn diagram of trying to minimize, achieve load balance while minimizing communication and maintaining good space and update costs. we're going to do a case study. I'm going to do a case study, spend most of the sort of technical depth of the presentation looking at the question that we asked was, well, databases rely on B trees. Okay, what is the PIM optimized replacement for a B tree? And that what we end up calling PIM tree. We'll talk about that. A key idea of PIM tree we'll talk about is this notion of push-pull search, which is interesting because it really says that, again, don't think of the world as a push-to-compute world. Take advantage of both modalities. Take advantage of doing the PIM thing and the von Neumann thing. What makes sense in our case, what moves less data. Okay, and that's going to be very useful for achieving this, addressing this inherent tension we're going to talk about. Then I'm going to sort of do a whirlwind tour of, very briefly, of a bunch of the other kinds of indexes we looked at, and also our design of a complete OLTP database, transactional processing database. And in all cases, you'll see that the goal we were trying to achieve was, we want this to run fast in practice. The platform we were using was the UpMem platform, so we wanted this to outperform, everything out there, but also have these analytical guarantees, right? That we could argue that no matter how skewed your workload looked like and things like that, we were going to achieve this good performance. Okay, so hopefully by the end of the talk, I'm going to put up the same slide again, and it'll all make sense. There's some front end, powerful, has a last level cache, things like that. And then there's the memory, the bulk of the memory is stuff that has processing power on it, right? So you've got, on the PIM side, you've got many of these PIM modules. Each of them have some amount of memory and a core associated with that memory. All communication, to keep it simple, we're going to say all communication goes back and forth through the CPU. There's no direct communication between the PIM cores. That matches the UpMem system. It's not really required, but it just keeps the things simpler, right? If you had a PIM system where the cores could talk to each other directly, it wouldn't change all that much about what I'm going to present. Okay. Usually early on, we had the question while Onur was speaking about what's the API. Because the thing about these, the other thing we really liked about the UpMem system is it's a general purpose core. It's a simple in order core. Okay, so you can actually do any sorts of programs there. It's not limited to matrix arithmetic, right? So max and things like that. The API is you have a command that will allow you to send the code to all the PIM modules, right? And then when you're ready to invoke that particular function or particular program, there's a command to scatter the arguments, right? You collect all the arguments on the host side, and you say, boom, send them, okay? And they go to each they go. You can send different arguments to each PIM. Then you say launch, right? And then the host side, is just hangs out, I guess. I mean, you could have it do other things, but there's sort of this check to see when the PIM modules are done. And then when they're done, there's a gather operation that allows you to collect the results of what the PIMs produce. Okay, so the PIMs only read and write their local memory. And so in order to pass them in arguments, you scatter into their local memory, right? And when they're done, you gather back from the local memory. Okay, so that's kind of the way it works. All right, so when we started thinking about this issue, which was, I guess, early 2020s, I observed that, thanks to people like Onur and his team, there were, and various efforts by others, there were already 100+ recent papers, like in the last decade, on PIM. It was emerging as an as was mentioned by Onur. You've got things like Hal Stone, writing papers in the 1970s. So it was a 1970. So it was a 50-year-old idea by 2020. But there was a resurgence of interest for the reasons that Onur mentioned in his talk. And that was fabulous. But then, and this is getting to Onur's point, he talked about the foundations of things. But in terms of how would you want to program things, how does this impact algorithm design? What are sort of fundamental things you can say about this kind of system? We only found 2 papers. Okay. Now Onur did write one of them, so 50% of it, but that's all we could find. Okay. And so what we concluded, and I've sort of already highlighted in my key takeaway slide, how we set about to think about the foundations of it, right? And the first question we were asking ourselves again was, how is this model of computation different? Because it's not really different. Then you just take the algorithms you had for some other, the data structures you had, or the application code you had for some other setting, and you just apply it, right? And then as sort of a foundational question, it's not that interesting, right? But at least in our framing of it, it's really these 2 asymmetric pieces that make it an interesting model. Okay, so we talk about a CPU side, which had a multi-core processor with this shared last level cache, a PIM side with these PIM cores, each with their local memory and network in between them, and then the UpMem system operated in these bulk synchronous rounds. It was the way to sort of avoid. It is the way to avoid, or a way to avoid coherence issues, right? Races between the CPU side trying to access the same memory that the PIM's accessing. So in the UpMem system, you can do one or the other, but not both at the same time. Okay. Now it turns out that this is the simplest programming model you can use for the UpMem style of systems. But you can actually do, and in some of the work we did, you can actually already do something more fine-grained. If you don't rely on their APIs, you can kind of rewrite things. Basically, in UpMem style system, the unit of synchrony is really the rank. Okay, and that's, well, I'll get into later why that's true. And so you can treat each rank independently and do things in parallel, asynchronously across the rank. But within the rank, you're kind of stuck. And I can explain more about that later. All right. So model of computation. So we had to have metrics. So on the CPU side, we said, well, we'll just use the standard shared memory metrics of work and span. Okay. Just as a refresher, why does that work on the CPU side? Because in a shared memory context, because if you do work stealing, then those are the metrics that matter, right? You can always maintain load balance by doing work stealing. And so this is the metrics that the community has settled on, right? And you say, well, why don't we do work stealing here? Well, work stealing moves data, right? You're stealing work. You got to grab the data that's associated with that work. Here, that's cheap to do. Across here, that's costly data movement. Then thinking about this side, the PIM side is a distributed memory world, right? What do you care about in distributed memory? You really care about, especially in a bulk synchronous framing, you really care about what was the maximum work that got done. Like what was the straggler, right? Which of the PIM modules was burdened with the most work and the most data in and out of it, okay? And so that's the notion of PIM time. Is the maximum work on any one of the PIM cores. And then we're interested in minimizing communication. So it's the communication volume, but you also want that to be load balanced, right? You don't want the straggler to be because a particular PIM module had to have a lot of data in and out of it to finish its work. Okay. so just to reiterate one more time, because I think this is important, a lot of the prior work had just focused on this side. Okay, in fact, you know, to be frank, some of Onur's simulators only cared about this side. Okay, and so you might think, well, why do I care about this side? Okay, I could just program as a distributed memory system and pay attention to that side. But it turns out that that host side is really useful, right? Just to give you a foreshadowing, as I mentioned, the PIM side is really bad at skew. Caches are really good at skew, right? If you have a small amount of data that everybody wants to touch, this is the side you want to do it, right? It's built for that, okay? So you don't want to throw the side away because it has complementary strengths that you want to take advantage of. Okay. So again, distributed memory with a powerful shared memory front end. All right. So I touched on this a minute ago, but you know, if you're going to push compute to data, compute to memory, then if your data use is unbalanced, like all the data that you want to touch is here, then that's hot and all these others are idle, right? In the extreme, you get no parallelism whatsoever. All right. We don't worry about that when we're programming a shared memory system because, again, wow, if you got all the data, if all the data use is concentrated, that's really good last level cache uses, right? So you're actually happy with that case. Here, you're very unhappy with that case. All right. And again, to sort of mitigate data hotspots by constantly migrating data, that kind of defeats the whole purpose of having PIM in the first place, right? If you're spending all your wasting all this data movement, hopping data from hotspots to non-hotspots and things like that, then you haven't actually avoided data movement. Okay, so that talks about this here tension between trying to get load balance so that no, you know, one PIM is a heavy straggler, right? You get good utilization across all the PIMs, but you're still trying to reduce communication. Okay. And there's actually a third metric because the thing is, if you really all you cared about is this, and it was like a read-only workload, you could, and you had plenty of memory, you could just replicate everything, and then every PIM module would have a local copy of whatever you needed, and you wouldn't have to worry about this, right? So the real third constraint is space efficient, right? You don't want to blow up. You don't want to use so many replicas of things that you blow up. And of course, with any system that has replicas, you'd have to pay update costs to keep, and you don't want that communication cost you either, right? So, and it turns out that these things kind of go hand in hand, right? If you don't have a lot of replicas, you don't have a lot of things to update and so forth. So, so that's the tension. All right. So now I want to make this concrete by looking at a particular case study I mentioned, which is what was the B tree replacement, right? So B tree is just an example, the most popular example of an ordered index. Okay, what ordered index means is it's like not like a hash table, you just do a key lookup. You actually have to be able to do things like range scans or just predecessor queries, right? Or successor queries. All right. And so that's what makes it that you have to have an index that preserves some notion of ordering so that you can find the predecessor key or find a bunch of keys in a range. Okay. And of course, we want these to support inserts and deletes, be dynamic. All right, so there was this prior work that did the most natural thing, right? I've got this index, it's ordered. All right, I'm just going to subdivide the range into pieces where there's, say, an equal number of keys in each piece, right? I'm going to take that subrange and put it on a PIM module. So in all my figures, the colors represent different PIM modules, right? Again, I'm only going to show 4. But think of the MEM system has over 2,000, right? I'm going to show trees as things that look like skip lists. If you're, you know, just think of any kind of tree that you want. Like it could be you know, you could draw something that look more like a B tree here. But we happen to use skip lists for reasons I can get into if there's questions at the end. And so what you do then is you say, what are the splitting points of this subdivision partitioning into range, and you store those at the host front end. And then when a lookup comes in, you just figure out which PIM module to set it to when a query comes in. Okay. All right. So that sounds great, right? And let's suppose I have a batch of queries that is shown. All right. Then what happens? Well, they all actually fall between 7 and 24. So they all want to go to this PIM module, and we have this problem I was mentioning, right? It's got a complete overload hotspot on that PIM module, no parallelism in the system. Okay. So the other extreme, if you want to get load balance, the other extreme is I'm just going to take all the nodes in my index, and I'm just going to scatter them randomly across all the PIM modules. Okay. And so, due to properties of randomization, that feels like it should resolve load imbalance problems, right? Any search path is going to, roughly hit equally likely hit all these different colors and so forth like that. Turns out that's not true. We'll show an example in a minute, but at least, first principles, first blush, this sounds like a good idea. But of course, it's a terrible idea for PIM setting because every path hops through a whole bunch of different PIM modules, wherever you go, right? And every time you change colors in these figures, that's a communication, right? And so that's a lot of data movement just to do each search. Okay, so that's terrible. So those are the two extremes. All right. So range partitioning is very space efficient. I didn't have to make any copies of things. It's great at communication. It's terrible at load balance. Random mapping, space efficient, load balance, terrible at communication. Okay. Full replication, right, would solve the load balance and the communication problems, right? But it's, you've blown up the space by a factor of P if you have PIM modules. So that doesn't work. So the question is, can you get all three of them at once? All right. And the answer is yes. Otherwise, I've wasted your time. So we had this thing we call the PIM tree, and I'm going to sort of build it up gradually. The first thing you observe is that, this is a tree. So most of the top, all the top levels down to certain level are tiny compared to the rest of the tree. All right. So I can actually afford to do full replication of the whole top part of the tree. Okay. So what we do is we go all but the last log P levels get fully replicated and stored on every PIM module. So it's only blown up the space by like a factor of 2, which we'll assume is reasonable. You can play with the constants if you like. And then when I get a batch of queries, I just spread them equally across the PIM modules, and they all get through without any communication down to the last log P levels of the index. All right. And then let's suppose for now that I just do random distribution at the bottom. Okay. All right. So that's nice. Now, the other thing that we need is we've got a lot of replicas here, so we better make sure that you don't update them very often. But it turns out in sort of any tree that's, where the updates propagate up from the leaves, particularly a skip list where there's only a certain probability that you'll ever get an update that goes up high in the tree, right? This part gets rarely updated, okay? And so you can amortize the cost of when you do have to update all the copies of this against how low the probability is that you actually even have to do that. Okay. Yeah, and particularly if you use a skip list with a probability of a half of being promoted to the next level. Yeah, if you're not familiar with skip lists, basically you just the bottom level you link list, double link list all the keys, and then every key gets to go up a level with certain probability, and then you just again hook together, double link list that, and so forth. Okay, and so the only way you get way up to here is if you log p times you flip the tail. Okay. So that sounds pretty good. We still have to sort of suffer some communications here, but it sounds like at least it's load balance, right? There's no load balance initiative here. This is random mapping. Surely this has got to be done, right? This has got to be good. All right. Well, let's look at this simple example here. Suppose I have predecessors 1, 8, 9, and 10. I'm going to send them, round robin, one each so that's good. They go through their complete copies of the top of the tree, and they send back to the CPU side. Here's where I need to go next, right? These 3 keys need to go to the node 0. These 3 need to go to the node 7. So if you did strictly the push the compute to data approach, you would look like that. Okay. Yikes. All right. So even though all these were randomly mapped, this guy still got hammered. All right. Okay. So so the solution to that is this thing called push-pull search. Okay. So what the CPU is going to do, the CPU has full information about what's about to be sent out, right? It's about to do one of these scatters. It knows exactly where the hotspots are, right? Again, a good use of the host front end. It knows where the hotspots are. Dynamically on the fly, it sees what's coming back and says, "Oh my gosh, want to go to node 7." So when you have a node that's not highly contended, you go ahead and do the processing memory thing, right? And so in this case, it pushes that query of 1 to node 0. And then instead of pushing 8, 9, and 10 to this poor PIM module that'd be so overloaded, and again, these are toy examples. Like you imagine, we deal with batch sizes of 1 million, things like that, right? We're trying to process 1 million queries at a time. Instead of having hundreds of thousands hit the same PIM module, we'll just grab that data and pull it the other direction. Do the normal von Neumann thing. All right. And that's basically it. So independently, at every step, for each node in the tree, figure out whether it's better to push the queries to the node or pull the node back to the queries. Remember, better means what moves less data. Okay. Host CPU, as I mentioned, is really great at small amount of data that a lot of work needs to be done on, right? So use it, right? And the general principle is exploit the complementary strengths of each side. Figure out which side is better at the task and try to do that side of it. Okay. So there's a couple other optimizations that we do in the paper. So we have the fully replicated top part. We have a randomized bottom part. We have a middle part where we do partial replication. I don't really have time to go into it, but basically it allows you to make it through this whole root to leaf index in basically three hops. Okay. All right. And then nobody would build a B tree with fan out 2. Okay. Similarly, we don't build a skip list with fan out, with promotion probability 2. We promote only with probably 1 over B, or B you can fix. We use B equals 16 in our experiments. And then you take all the nodes that are like if I decide to pack these 4 here into a single node, I would just pack it into an array. Okay, so I can fetch it very efficiently instead of having all this pointer indirection. Asymptotically, this reduces the total communication to log base B of log base B of P. If you're not into asymptotics, this is 3 in practice. Okay, you could have 1 million PIM modules, it'd still be roughly 3, right? It'd still be 3. Okay. And again, the code is all open source. Okay, so so therefore we were able to hit this sweet spot, right? there's and prove properties about the communication and the load balance and all these kinds of things. As long as you have a batches that are some minimal size, the size only depends on the number of PIM modules and that the parameter B. So it's not that big. Say, think of like 1 million or 100,000 is fine. Okay. For the people that are theory oriented, the way this works out, the way the proofs work out, is we use these tossing weighted balls in the bins style of analysis. Okay. And the thing that matters is how heavy is how lopsided is the heaviest bin, right? The heaviest ball. How big is that ball that you're trying to throw randomly? Gonna impact things. And it turns out that as long as that heaviest ball is below a certain threshold, then with high probability, all the bins, i.e. all the PIM modules, will get a balanced amount of work. Okay. And the way that we're able to bound the weight of the biggest ball is by doing push-pull search, right? Because if the ball is going to be really big, we say, oh, well, that means we should pull, right? We don't do the processing memory thing at all for that ball, that equivalent of a ball. All right, good. All right, so then we ran on the UpMem system. This is and again, we mentioned the API it uses. You can see it was the multi-core CPU at a 22 megabyte cache. The PIM cores are 32-bit RISC processors running at 450 megahertz, so much wimpier than the multi-core CPU. And really, the main difference between the analytical model we're using in this system is that not all the memory is PIM equipped, right? It's configurable on a per memory channel basis. How many of the memory channels in the architecture do you devote to just passive DRAM versus PIM equipped DRAM? Okay. All right. So how did it look? So this is throughput. Okay, predecessor queries across. In this case, we also did real workloads. This is just showing a synthetic workload where you're making things more and more skewed as you go left to right. For those who may not be familiar with the Ziphian, most people probably are by now, but like Ziphian 1 is like the distribution of words in say the English language, right? There's actually and like Twitter cache traces, there's a paper from OSDI a few years back that said that 95% of their workload traces were Ziphian 0.4 or higher, and half of them were Ziphian 1.2 or higher. Okay, so I say all that to say, yes, our system, which is the yellow, is losing at really low skew cases, but as soon as you get to real world skew, we're winning. So we're winning by 1.8. Higher throughput at 0.4, 32 at that words in English language range, 59 at the next bump up, and it just gets the number just would go and grow, right? Because the prior work is not skew resistant. Okay, so even in this range of ZIF parameters here, we get up to 59x improvement. All right, so that's against the prior PIM-based solution. All right, so the question is, well, is it even worth using PIM at all? All right, so that's this graph. And this is again showing throughput, so higher is better. This is on a Wikipedia data set. So here, this again is our PIM tree for search and for index. This is predecessor and insert, predecessor and insert. And we're comparing against two state-of-the-art CPU-based in-memory indexes. Right, an AB tree and a balanced Bronson BST, and we are showing improvements. Right, we're outperforming the CPU-based version. Okay, we're faster than CPU indexes, and what I'm not showing you is that the amount of memory traffic memory channel traffic, the data movement cost is 3x less. Okay, so we have significantly less communication, and we're faster, higher throughput. All right. And this is the first generation PIM system. I mean, if we have time, I can tell you all the warts of that first generation PIM system and how it made our performance suffer in ways that aren't fundamental to PIM. But again, these are the the worst, the lower bound on what the numbers will end up looking like if you have beyond a first generation PIM system. Okay, so that was the deep dive in PIM tree. Now I just want to do a bit of a whirlwind on some of the other things we looked at. We looked at radix trees, so string lookup kinds of things. There, the key challenge is that whereas a skip list or B tree or whatever are balanced search trees, string tries, radix trees, the shape of the tree depends entirely on what you insert into it. So you have no control over making that thing balanced or not. And so that was another sort of the main challenge, was figuring out how to get how to preserve our good ideas about load balance across a tree that was highly highly imbalanced. We also looked at space partitioning indexes. I have a couple examples here. This is the KD tree, which is you pick a dimension and then you find the median point, just considering that dimension, and you split the space that way, and then you recurse on both sides and so forth. So that's one way to do that. That creates a nice balanced space index. So spatial indexes are things like you want to find nearest neighbor points, or you give a region, you say how many points fall in this region, things like that, right? So that's really good for balanced tree, but the problem is that there's rebalancing operations that are really expensive. A spatial index that doesn't require rebalancing is the ZD tree. Okay, that is sort of, you take the coordinate space and you follow a Z ordering to linearize that space, and then you build the thing from there. Here instead of splitting at the median, so this divides the data in half, you divide the range in half. And so here this can be highly imbalanced. Okay, but you never have to pay for rebalancing, so it has that advantage. All right, so I'm not going to describe the algorithms, but I will show you the results, or sampling the results. So so the PIM-ZD tree was ours. The PKD tree and the ZD tree are the state-of-the-art shared memory implementations. And so this is throughput, so higher is better. This is insert box count. You give it say a rectangular box, and it tells you how many points. Box fetch, you fetch all the points. Nearest neighbor, 10 nearest neighbors, 100 nearest neighbors, and so forth. So, and this is the OpenStreetMap data set, and this is a uniform data set. And you can see that for the most part, we are doing better than the CPU solutions. But there's things like the 100 nearest neighbors where, again, the sort of the communication cost of collecting a range that's scattered across where the entire space of interest for a query may not lie within the PIM module, you start to see some pain for that. Okay. And again, I'm not showing data movement, but we have 5 times less data movement. Okay. And in fact, when we set out to do this, we are convinced we're going to be able to reduce data movement, keep things load balanced and so forth like that. And we say we're just trying to match the performance of the CPU. If we actually get better performance of the CPU while reducing data movement by 5x, that's just like a bonus. And so we're often surprised or happy when we do even win on the throughput. So this is just showing what sort of scalability guarantees by you, right? So this is, we're taking the base data set and increasing it from 20 million, 40 million up to 300 million, and running our ZD tree algorithm. And what you see here is that our performance is flat, and the performance of these other techniques drops. Why is that? Well, our performance has nothing that depends on the data set size. It's all depends on the number of PIM modules. Okay, so this just is an experimental, and that's not true for these other two. This is an experimental demonstration of that the asymptotics actually pays off. The analytics actually pays off. Okay, so as I mentioned, processing memory is not a new idea. Database community has considered, there was like a whole period where there's these active disk proposals. We have computational storage devices now, right? There's some computing done at disks. But the conventional wisdom has always been that what PIM is really good at is filtering, right? It's taking a bunch of data, applying some sort of predicate to it, and returning just the small amount of data you actually care about. And then that's the big win. You avoided the data movement of bringing all those data, all those database tuples, database rows back to the front end just to throw away all the ones that didn't fit the thing. On the other hand, nobody was thinking about doing transactional processing instead, right? So filtering is a analytical operation, right? OLAP operation. Because who in their right mind would try to do transactions on a PIM system, right? I mean, you've got these very tight latency constraints, and there's no filtering involved. I mean, it's just like, it's crazy, right? But we're contrarians, so we said no. We've got indexes. We figured out how to do indexes. That's the bottleneck of OLTP. So if we've solved indexes, we can solve the rest of it. All right. So this slide talks about if you traverse a tree, an index like a B+ tree, in the non-processing memory world, then you're going to move all that data, fetch every hop through the tree. You're moving it back. I mean, maybe the top level or so is already cached on the CPU, but most of the levels of the index are going to have to involve data movement. All right. But as we just saw, if you do in the PIM world, then there's, most of the action is on the PIM side, and there's very little that goes back and forth, right? And so you can calculate those kinds of quantities, and then just say, if the one side is a lot less data movement than the other side, you want to, do the side that moves less data, all right? So you have a large advantage of using processing memory if you have that sort of what we call near memory affinity. Okay, and so you want to put your indexes on PIM. Databases also have are multi-versioned. Okay, pretty much all databases of note of multi-version, so that you can do updates at the same time as you're doing reads, and everything stays consistent. That means for every data item in your system, you have a bunch of versions of it that are time-stamped in some way, and your query goes to one of those. So that's called a version chain. But again, it's pointer chasing. So you want to do that all on the PIM side. On the other hand, if all you're trying to do is fetch a tuple, like the index has told you, oh, this is the tuple you want, that's actually, there's no savings on the PIM whatsoever, right? In both cases, you fetch the tuple. Okay. So fetching tuple, you want to do on the DRAM side, the passive DRAM. Okay. So basically, on that principle and a bunch of other optimizations, we built the OLTP PIM. Okay. This is kind of a busy slide, but the PIM side, again, we had the indexes, we had those version chains. The DRAM side had the tuple. The CPU engine did all this transaction management stuff, and the logging and the aborting and committing and things like that. There were some interesting things about doing garbage collection and so forth. But in the end, it came out pretty nicely. So in memory traffic, so this is on the YCSB. This is the read 95%. This is read 100%. This is probably the more realistic one. We're 5 and 6x less memory traffic, right? Memory channel traffic. So that was a nice confirmation of what we were hoping to find. But we also wanted throughput. So we were pleasantly surprised that we're actually 70% faster than. So this is the state-of-the-art academic in-memory database system. It follows a long line of previous works to sort of be the pinnacle. So this again is showing that one, that there is benefit to using processing memory for this kind of workload, right? And two, that our techniques for extracting the value were paying off. Okay, so I talked about that. This transactional latency issue that led people to not think about doing, or the lack of filtering, not think about doing PIM. Our latency is worse. So this is the latency, if you want to think about it. This is varying batch sizes, like how many how many queries are you processing at once per thread? But nevertheless, our latency, where the start point is under 10 milliseconds, where the prior system was maybe 50x smaller than that. Our argument is we're higher throughput, and that 10 milliseconds is good enough, right? It's under 100 milliseconds, which is sort of the threshold at which people start to notice, and so the latency is good enough. Okay. One of the reasons our latency is higher is because we're taking these huge batches, right? And so the queries wait to get the whole batch done. But again, that's a trade-off here. So you can see the red is our throughput. This is where we're getting the best throughput. We could have even lower latency at lower throughput, but and certainly save memory traffic. But if we wanted to beat the throughput of the in-memory, the CPU version, we would need larger throughputs, larger batch sizes, which leads to higher latencies, but all within the under 10 milliseconds. Okay, how much time do I have? What? 12 minutes? Okay, good. So I want to finish by talking about this thought exercise we had. We said, okay, so part of what's going on with all our techniques is that we have this coordinator that's doing all this action, and this is the sort of coordinator worker kind of setup. Why couldn't we just, if you had a distributed system, just elect one to be a coordinator and have them run these algorithms? Okay. So why not just elect one of the machines to act as a host and then run our algorithms? What would go wrong? Well, as I touched on in the key takeaway slide, that host is actually really heavily worked, right? It's got to send out all the work, including all the queries, the data, everything, not the data, all the tasks that the PIMs need to be able to do, and it needs to absorb all the results when they're done. Okay, and so that's pretty heavy duty, right? Well, that makes a lot of sense in the UpMem style of world, right? That basically you've got a front end processor, it's got its memory. You would never build a memory system. I mean, forget the PIM core part. When this original machine was architected, you want the bandwidth in and out of this host to not be the bottleneck, right? And so to make the system balanced, you had to make it the bandwidth out of this node to be equal to the bandwidth into all these nodes. So another way to think about that is that the host has P times the off-chip bandwidth of a PIM module. Okay, and moreover, we need that host to collect all the, do all this processing, get all this information with the PIMs, quickly process and put it out there. So it's got to be more powerful than these PIM cores. And so here's I don't have a, you know, all I can show you here is the data. So here what we're showing is that the time spent, if we turn off the pipelining on each of the components, PIM execution, communication between the two, function loading, and CPU execution. Okay, and so the red part, which is the part the CPU is doing, right? And the yellow is the part the PIM uses. And notice they're kind of the same, right? That basically if the CPU is being overwhelmed, the red part would dominate, and it doesn't. Okay, so that shows that the system has such that the power of the host CPU can keep up with all the PIM modules, what they can all do, right? That the union of all the PIM execution is on par with what the CPU can do. Okay. All right. So so that's the key, that the host is beneficial. So if you're thinking about other possible PIM configurations, and you want to do at least some of the techniques that we use, keep in mind that that host needs to have asymmetrical high computing bandwidth, or you may not be able to really take advantage of all these good things that you know, that we've shown. Okay. So here's the team. The first paper was during the pandemic. So this was the student giving the talk, and then I just put all the other authors' pictures on there. So again, hopefully this slide now makes sense, right? The key takeaways: the PIM is unique as a way of doing computation because of this combination of a shared memory host that has asymmetrical high computing bandwidth, and the distributed memory part, which of course is where you get all the memory data movement savings, right? We have a model of computation that you can look at to think about how to optimize for this kind of thing. There's always going to be an inherent tension between load balance, communication, and space, assuming your workloads have any skew at all. But there's ways to resolve that. Push-pull search, I think, is a highly applicable idea to all sorts of PIM settings, right? Just think about what moves data, what moves less data, and do that, right? Or more generally, you know, take advantage of the complementary strengths of each side, right? We know that the host front end is great at dealing with a lot of work on a small amount of data, right? Because it all fits in the last level cache. I've shown you a whirlwind tour of the other kinds of indexes that we did and mentioned some of the challenges we had to overcome, and that we're actually able to do an entire transactional database and kind of bunk conventional wisdom that nobody would ever want to do transactional database on PIM. PIM is built for filtering. Transactions don't have filtering. That we've you know, been able to achieve both faster in practice, at least on the Upman platform, which is the one we had our hands on, and also have things be guaranteed robust against you know, and scalable, right? So that's always a nice combination. All right, with that, I'll take questions.
So main point slide before was that we could get to care the bandwidth of the host to keep up in modules. So with Upman, I can believe it's not that hard, right? How do you see it in the configuration where you have CXL connected multiple PIM modules with even more PGs?
Yeah, so again, if the system is balanced in the sense that it's designed to support the highest throughput that you can try to achieve. Like it's designed so that the sort of what you can get off on and off the host matches what can be delivered, then we should be, it should be okay. Now, the system, what you're pointing at is that if the processor, if the amount of bandwidth, the number of memory channels and such doesn't grow with the amount of disaggregated memory that you hang off of it, then yeah, you're in trouble. But this thing, it degrades. It's not a cliff. It degrades gracefully, right? Basically, you just, you get a proportionate slowing. Yeah, yeah. Yeah, that's true. Multi-socket would. Ah, see, I anticipated this. Okay, so so again, the thing that we really liked about UpMem was the scale, right? The fact that they had these 2,500 of them, so you could actually do things where the scale mattered, or you had to do things where the scale mattered. There's challenges with scale, and the fact that you could run general code, right, which is not where the industry is headed at this moment. As a first generation system, it had a bunch of challenges. One of the reasons that our batches had to be so large is that the offload cost, that switching between allowing the PIMs to run and then having them stop and then allow the CPU run is very high. Okay, and so what that means is it requires very large batch sizes. Like I said, the experiments I was showing you were like we'd have 1 billion keys in our database and we were running 1 million or half a million or a million batch sizes in order to try to amortize this very high overhead. Okay, I don't see any fundamental reason why that overhead was so high, and so it feels like that should be easy to fix. As a result of having to run very large batch sizes, if you wanted to amortize this overhead, you actually blew out the last level cache of the host. The host only had 22 megabytes of last level cache, and you needed to fit a bigger thing. And so what ended up happening is if you really wanted to, they're diminishing returns, right? If you really wanted to send a larger batch, you ended up taking all these cache misses just to collect the batch, just to form the, right? You're creating all these, this set of buffers, one for each PIM module, of the data you're about to send them. That's the batch, right? Like I'm gonna send this query, I want to send all that thing. That has to be so large that collective buffering was larger than the last level cache. And so when you gave it the scatter command, it had to go to the normal passive DRAM and refetch the thing you just stuck in the buffer, right before that. And so it's like cache miss upon cache miss upon cache miss. So the actual memory traffic, there's a noticeable amount in these numbers of memory traffic that's actually not memory channel traffic that's just doing that, collecting the thing from the buffer. Okay, so if you can make this smaller, then this probably won't be a problem. Alternatively, you can make this larger. There's certainly plenty of front ends with more cache. The APIs, there's nice APIs they provide. They appear to have gone for generalization. They wanted, for instance, I don't know, the PIM system to be multi-user at once or things like that, right? So for the things that for us were the common case, like the whole thing is doing what we're doing, right? We're not worried about only using quarter of the PIMs for this and 3/4 of the PIMs for something else. So we actually rewrote a lot of the APIs to do that. What for us was the common case, like the whole machine is ours, you know, boom, go at it, right? So that we did quite a little bit. There's only 24 kilobytes of IRAM. IRAM is you load the programs into that in order for them to execute on each PIM module. And so what that meant for complicated things like databases, we're paying, actually you probably saw it on one of my earlier slides. There was like this piece that was was like program loading. I forget what I called it, but it was a noticeable fraction of the execution was just, oh, now we got to run this part of the database, you know, this part of the transaction. We have to swap in all that code, right? So that was a pain point. The limited synchronization. So again, you know, it's a trade-off, right? If you're designing for something that's going to fit on a bank, right? You get very limited area. You're very probably trying to hit a cost point that's not very high, things like that, right? There's a lot of constraints on that. You know, as opposed to say you wanted to do something per rank basis, right? Where you got a lot more area, you could, you know, whatever. But on a per bank basis, so the one of the things that they provided very limited support for was synchronization. And you say, well, why do you need synchronization? It's on a PIM core when there's only the one PIM core, right? And so you basically, when you got dedicated access to your local memory. Well, I didn't tell the whole story. The whole story is that to do latency hiding, the PIM module does sort of the old HEP style thing, if you remember your architecture history, where you cycle through a bunch of contexts, right, in a fixed order. In this case, it's like a dozen or whatever, so that by the time you get back to you do 12 loads. By the time you get back to the first load, it's ready to go, right? So you actually have a race between those threads if you're trying to do things like update an index while other queries are going on and things like that, or just multiple updates to the same index on the part of the index that's on that node. You need synchronization. And so if you do that on the CPU side, it's fine. You could do fine-grained locking because you'd have unlimited supply of lock variables. They had I can't remember if it's like 24 or something. There's some fixed number of things you can use as lock variables. And so when we did when you're trying to do these kinds of safe updates to parts of an index, we're forced to do coarse grain locking, right? Which meant that you grab a lock and you grab a lock on an entire part of a tree, and that would prevent a lot of concurrency, right? And so we suffered. You can see it in our paper. We suffered for workloads that were transactional workloads that were write heavy. For instance, we suffered because we were forced to do, not because there was something inherently hard about or slow about doing writes in PIM. It was just we had to grab coarse grain locks instead of fine grain locks, and that serialized a lot more than what we had, what you would like. Okay. Do you agree with those limitations, or probably found others? Yeah. Got to get back to it.
Cannot extend the display. Now it's accepted. I think, yeah, we're waiting the tangentially center slides. Very good.
PD, sorry, as a PowerPoint.
Yes. Can't you just say directly from an email?
Oh, okay, just add you here.
No, can't you just directly send this to my email?
Yeah, what's it?
Okay.
A lot of audience. There's not much I can do now.
Yes. We're arranging the. And can I? See.
And
Yeah, you can.
and this.
And this is for you.
Yeah. Yeah. Yeah.
I need to log in my SharePoint thing.
Open.
No, it's waiting my code because it's you
Okay.
shared directly.
Maybe check spam.
Okay.
Yeah. I hope Onur doesn't come back before my presentation. Oh no, this is being like. Does he? Never mind. It's okay.
How can
That's
I
good.
download this?
You can just present here, right? It says present. Do you have a clicker?
Yes, here.
Okay. Yeah.
Let's who is that?
No, sorry. Wait. Can you just edit it? Just the title is so terrible. Sorry. Yeah.
So is it here?
Yeah. Okay.
About yes. Makes sense.
Mm. Okay.
Hello, everyone. So this will be the third talk of this session. So eventually we'll present diffuse speculative law of microfusion. Eventually Nisa is a PhD student Electrical and Computer Engineering Department at CMU, advised by Professor Akita Sriyaman. Her research focused on designing efficient computer systems, bridging computer architecture and operating systems to enable high performance and sustainable hyperscale data center solutions across the compute stack. Feel free to.
Yeah, okay. Hi everyone, my name is Deepanjali and today I'm really excited to talk to you all about my project titled Speculative Load Micro-op Fusion. This is joint work with my advisor and collaborators across Columbia, AMD and UCSC. Okay, so data centers applications run across millions of servers, serving a variety of applications such as web search, social media, or e-commerce platforms. So the takeaway here is improving the performance of these processors is important to enable efficient execution of these applications. But the question is, what causes performance bottlenecks in these applications today? So here in this graph, I'm showing a bunch of applications in Google's applications, such as search or email, and the x-axis shows the percentage of processor cycles spent being back-end bound. That means they're being stalled and not executing useful work. This is prior work from Google in 2015. Onur showed the same graph in a different version in his talk. So the takeaway here is these applications spend about 40 to 60% of their processor cycles being back-end bound. So the question is, how can we reduce these back-end stalls? So here I'm showing a graph from prior work that shows potential benefits in terms of performance when we reduce the data movement bottleneck across various levels of the memory hierarchy, specifically by data prefetching. So the takeaway from this graph is, as you can see, there are two really high bars, one that shows 9% performance gain and the other 13%. So in this work, we're focusing on the first one, that is reducing the data movement bottleneck between the L1 cache and the processor. Yeah. So there's several ways to reduce this backend stalls, and one promising way that we are focusing on is called load micro-op fusion. So just some context, memory loads are broken down into simpler operations, which are called micro-ops. And this fusion is essentially merging these simpler operations. Let me just walk you through what it looks like. So a processor without fusion. So here's an example. So here are two assembly instructions that perform memory loads, and they translate into two different load micro-ops. And here's the processor and memory, and the processor would issue two separate requests to fetch the data. But in a system with this kind of fusion, the processor would essentially merge these two load micro-ops into a single micro-op that's supposed to perform the work required by both of these load micro-ops, essentially prefetching more data from the L1 cache. So the question is, how valuable is fusing this load micro-ops? So here in this graph, so on the x-axis, I'm showing a bunch of applications, which is a combination of database applications like MongoDB and Postgres, and graph analytics applications like breadth-first search and depth-first search. And the y-axis shows speed up percentage. This is compared to a system without any kind of fusion. The takeaway here is, on average, this kind of ideal fusion achieves around 9% of performance benefit. So this shows that fusion as an optimization shows promise for future processors. But the question is, how close are we to achieving this ideal case of performance benefit? So so in this graph, I'm showing applications again on the x-axis, and y-axis shows the performance gains. This is the same graph I showed in the previous slide, but with one additional bar, that is this pink color, which is called Helios, which is a state-of-the-art in load fusion mechanism. And the takeaway here is this current state of the art achieves around 13% of performance benefit of this ideal case of fusion. So the question we focus on is how do we approach this ideal performance gain with load micro-op fusion? Specifically, are there predictable parameters related to these memory loads that we can then use to guide fusion? So here's an example. So these are the two same assembly instructions I showed earlier. And say they're fetching data from a given memory region, say cache block, which is typically 64 bytes. And this first load, say, accesses the data at the start of the cache block at an offset, say 0. And the second one accesses at an offset of 8. Here, this offset delta would mean 8 bytes. The reason I'm defining this term will be clear in the next slide. So basically, in this talk, I'll be talking about three things. First, a characterization of identifying fusion opportunities. Second, our proposed mechanism to perform fusion based on our characterization. And finally, discuss our results. Okay, so first, the characterization. The question is, so I briefly talked about what this offset delta means. So in this particular characterization, we focus on how predictable is this cache block offset delta. The intuition is two loads that access a given region, say cache block, are fusible because the goal is to reduce the number of accesses we perform, and this fusing loads accessing same cache block allows us to do that. So these two loads access the same cache block, but what they access is different, and this cache block offset delta allows us to predict that. So here in this graph, I'm showing on the y-axis occurrences of this cache block offset delta, and the x-axis shows each fusible load pair. So here in this graph, having more points closer to the 100% means this parameter is more predictable. And the takeaway here is we find that across our evaluated applications, most fusible load pairs have this cache block offset delta as predictable. So now that we know that there's a parameter that's predictable, we use this to design our fusion mechanism. So here's a high-level overview of our proposed technique. So it's composed of three phases. So in the first phase, this deep fuse profiles applications to generate a memory access trace, which contains information such as the memory access, effective memory address, the memory size of this load, and the program counter. This memory access trace is then used to perform an offline analysis that identifies fusible load pairs and generates a set of fusion candidates. In this graph, I'm showing program counters. A natural question might be, why am I not just tracking the complete memory address? And the reason is this fusion happens in the processor front end, and we do have access to the program counter, which acts as a proxy for identifying fusible loads. And we then feed this fusible program counter pairs into the runtime system, which can then guide fusion based on this offline profiled data. Okay, so moving on to the next part of my talk. So now I'll discuss some results. So the x-axis shows applications and the y-axis shows the speed up in compared to a system without any fusion. So here are three bars. I already showed two of them. That's the teal color, which is an ideal case of fusion, and the pink one, which is the state of the art in fusion. So this lime green color is our proposed mechanism. And as shown in this graph, deep fuse is able to achieve around 7% performance gain compared to an ideal case, which achieves around 9% performance gain. Just a supporting graph, like what does the impact on backend pipeline resources look like? I'm showing a graph that shows the number of accesses to this L1D cache, since the motivation was to reduce the number of accesses we perform. So x-axis shows applications, and the y-axis shows this reduction in this number of L1D cache accesses we perform. And the takeaway here is, on average, Deep Fuse is able to reduce 30% of L1D cache accesses. Yeah. Okay, so just to conclude, in this talk, I presented a characterization that helped us identify a parameter that we then use to design our profile-guided speculative fusion mechanism, and finally discuss some performance gains from that. Yeah, thank you so much.
Wondering how many are you
Oh, that's a good question. So in this work, I focused on okay, so the question is, like, how many instructions can you fuse at once? In this work, I focused on fusing load pairs, but I did perform characterization to explore opportunities beyond pairs. For these applications that I evaluated, around 30 to 40% of loads did have opportunities for fusing 3 loads at once. But I've not explored that more. Yeah.
And then the characterization, you say that you can fuse them only if they're independent, right?
Can you repeat the question? What do you mean?
I think one, you can only fuse independent loads, right? Independent loads. So I think I did understand how it works. Like, how do you know which loads if you don't know it?
I see. So the question is, how do you identify dependencies and ensure that fusion was correct, right? So we do have hardware. So once the effective memory address is computed, we then check whether this fusion was correct. And if it wasn't correct, there's a pipeline flush. So yeah.
And lastly, the translation between PC to micro is very ISA specific. So did you test across, is the performance better for some ISAs across different ISAs?
So in this work, we focused on x86 processors. But no, I have not checked across ISAs. Yeah.
Any other question? So maybe I'll ask one. So this is a very, let's say, processor-centric technique that can help with take-home time. How do you think that that could be extended to memory-centric systems?
Right. That's a good question. I have been thinking about that. So one thing that seems interesting is, so in Onur's talk, he talked about how activating DRAM rows also consume energy. So perhaps fusion optimization applied there would likely perhaps identifying loads that access data within a given DRAM row and prefetching them so that you don't have to frequently activate each row might save some performance and energy benefits. Yeah.
Thank you. Any other question? Then let's thanks. Brian's Bond. Brian Bond is a fifth-year PhD at UC working under Professor Sohail. His research interests are in the broad area of computer architecture with particular emphasis in memory and storage systems, as well as accelerators for scientific computing and database systems. He is a Mavis Spiritual Faculty Fellow and has won the YUCCS Outstanding TA Award. He received BS in Computer Science and BA in Chemistry and Masters in Electrical Engineering, all from the University of Products. For more information, please visit this website.
I'm going to HCDS. Will also come. Thanks. It's fun. I enjoy it. So, architecture conference is not the best venue. They ask you questions at a very high level. So I think collaborators are the best people to ask you questions.
Yeah. But I think what I find interesting about conferences is seeing where their question comes from. Like how their context leads them to ask the question that they ask.
Like I was asked question. So every question I was asked, I've thought about. One of them this morning was like, how do you fuse unaligned? Now, what are opportunities?
So the next one is Yilong. Yilong, are you here?
Yeah, I'm here.
Can you share your screen if it's possible?
Yeah. Wait a minute. Oh, it's
Let me, okay. Do this.
yeah.
All right. Let me clear. Okay. Yilong Zhao is a PhD candidate at Shanghai Jiaotong University, advised by Professor Li Jiang. He is a member of the Advanced Computer Architecture Lab, and his research focuses on processing in memory architectures and AI accelerators. He receives his master's and bachelor's degrees from the same university in 2021 and 2028, respectively. Feel free to start, Yilong.
Okay. Hello everyone. I will mainly talk about our work in PIM. It's published.
Something happened. Yilong? Hello?
Hello. The I
We
I
hear
can
you.
hear I can hear some voice, some.
I don't know. I think you can continue.
Oh, okay. I will mainly talk about our work in PIM. It's published 2 years ago at ISCA 2024. And I will also give a brief introduction to our new paper, Push Step. My colleague will also present it on March 2025 at ASPLOS 2026. So I only introduced the background and key insight here. I'll first present the PIM. This page gives an outline of the paper. The paper tried to solve a data layout conflict when, between the CPU and PIM. CPU access memory in an interleaved order, while PIM only access the local banks. The key insight of this paper is to design a uniform memory space with CPU and PIM pages coexist in the space. So compared to the current design with a dedicated PIM memory space like a map, we do not need additional data movement. The paper solved 2 challenges. The first one is the coexistence of the 2 pages, and we propose a memory management method with software. The second challenge is the different layout of the 2 kinds of pages. We propose a hardware-based solution. The simulated result shows significant workload speed up because we eliminate the data movement. Then I will go through the work. In current computers, the memory interleaving is used to improve CPU bandwidth. And this figure gives an example of the channel level interleaving. Adjacent data blocks are mapped to different channels so that they can be accessed in parallel or with pipeline. The memory interleaving is achieved through address mapping. For example, if we map the lower order bits to the channel address, so the adjacent address are interleaved across the channels. As DRAM have many hierarchy levels, and the levels have different switch overheads. So the most efficient way is to map the higher space to the levels with higher switch overheads. So these levels are not switched frequently, and we can achieve a better bandwidth. Usually, row have the most switch overheads, so it's mapped to the highest order bits, while channel can be accessed in parallel, so they are mapped to the lowest order bits. This memory interleaving will severely damage the PIM performance. Suppose PIM compute on a contiguous block of data. In current compute systems, the data block is divided into pages, and the pages are mapped to some physical frames. And also, each page are further interleaved across the banks. So suppose the PIM is in the bank. From PIM aspect, it can only visible to some contiguous bytes. Typically, in each offload, the CPU need to transfer the address to PIM and invoke all the PIM computation. This is a microsecond level overhead. But in this case, in each offload, PIM can only compute with 1 byte because it does not know the second byte's location. So we need to offload tiny PIM workload many times, and this incurs large offload overhead. So PIM prefers to map a longer contiguous block of data to the same bank, so we can do the task with only one offload. This can amortize the offload overhead. The corresponding address mapping is mapped according to the DRAM hierarchy. The inner level is mapped to the lower order bits, and so they are adjacent in the hardware location. And this address mapping is completely different from the CPU's memory interleaving. To ensure offload efficiency, the current work isolates a dedicated PIM space from the CPU main memory. The PIM space is not interleaved, and CPU main memory is still interleaved. This figure shows what happened with the isolated design. A PIM workload typically can be divided into 4 phases, which is marked right here. In the first phase, CPU compute, and we get the result. Then in the second phase, we need to transfer the result data to the PIM space. And after PIM compute the result, we also need to move the result back to the CPU memory. So here we introduce 2 additional data transfer in this step labeled 3 and 5. In the transfer, we should first relay out the data because the source and destination have different layout, and then we can do the data copy. As shown in the previous work, for some of the tasks, this data transfer may dominate the total execution time. So some of the previous work also switch off a part of interleaving, for example, channel and rack. So we can save the layout computation because we do not need to relay out the channel and rack level. But this method may damage CPU bandwidth because the 2 levels are not interleaved. Moreover, even with this method, the data layout overhead still accounts for about 70% of the data transfer. So this slide is a summary. With single data layout in each memory space, the current 3 design cannot concurrently achieve the low offload overhead, a high CPU bandwidth, and low data transfer overhead. Our key insight is to enable 2 data layouts in the memory space, and we can achieve all the 3 goals. There's only one memory space, so we don't need data transfer between memory spaces. We still face some challenges to design the uniform space. the two challenges is contained in the inside. The first one is the coexistence, and the second is the different layout. This figure describes the first challenge. CPU page should be randomly mapped and virtualized, while PIM page should be mapped contiguously inside each bank. We should make them coexist in the space. This is the solution. We keep the management of CPU page the same as the current system, and we proposed a management method with huge page for PIM. In current system, to maximize the CPU access bandwidth, the row is mapped to the highest order base because they have the high switch overhead, and we keep this configure. So on this configure, when we allocate a PIM page, we allocate a huge page. We let the huge page large enough so the huge page is evenly distributed on all the banks. And this means that we allocate a page for every PIM. So the difference is that inside each PIM page, the address should not be interleaved. So this is different from the CPU page, and this is our second challenge. The second challenge can also be divided to two levels. In the first level, is the cache line layout in the page is different. Because cache line is addressable, so we can use the idea of dynamic address mapping to implement the two different layouts. Besides, the cache line of these two pages is still not the same. For CPU, the cache line is across all the devices, so it is equal to the DRAM burst. But for PIM, the cache line is on the same device because it's contiguous inside the bank. So it's not equal to the burst. To solve this, we propose a hardware-assisted method for transparent layout. This is an overview of our solution to the second challenge. For the first level, the dynamic address mapping can also be divided into two sublevels. The level divided by the DRAM bank. For the level above bank, it's include the channel rank and bank. We configure the memory controller to implement the dynamic address mapping, and it does not require hardware modification. We add two address alias in the memory controller and set it to the two different address mapping. The memory controller will select the mapping rule according to the page type. If the CPU page, it will go through the left rule, tag 0, and otherwise it will go through the tag 1 with PIM mapping rule. Well, here, some of the levels below bank, including the device, the row and column. The device is not addressable from the memory controller side, so we do this in the second solution. The second solution is to the dynamic address mapping with the levels below bank. We add two hardware modules, RCL and ATM on the DRAM side. This is a detailed figure. The RCL contains the PIM page numbers that we already allocate. When we access an address, the RCL will compare it with those address stored in the RCL. If it hits, so it means that the address is belong to a PIM page. We use the ATM module to convert address to the real hardware address. Otherwise, the address belongs to the CPU page, and we bypass the translation step. So we can dynamically map the address according to the page type. Then the second level is inside the cache line. As we call the challenge is the PIM page cache line is not equal to the burst. For this challenge, we also add a hardware named RC inside the DRAM side to solve this challenge. This is the hardware RC in the DRAM side. It is constructed with 8 subbuffers. Suppose we read this cache line from the device 2. And in this figure, each small block presents 8 bytes. In the first cycle, we load the burst from the DRAM to the subbuffer 0 of RC. Then in the second cycle, we load the second burst to the subbuffer 1. And after 8 cycles, all the 8 bursts are loaded to the RC. And then we can extract the cache line, the 220 to the 27, from the device 2 and put it to the memory bus. So we can get this burst. We can get this cache line. This is a summary of the architecture design. We propose 2 techniques for the 2 challenges. We only do software modification on the CPU side and hardware modules on the DRAM side. All hardware modifications are on the DRAM side, so it have full compatibility to the CPU SoC. You can find more details about how we accelerate the CPU access PIM pages using a software-hardware co-design solution. You can also find some other details in the paper. We evaluate YunPIM with RMM for PIM unit and Gen5 simulation for CPU overhead. We choose CPU workload and PIM workloads as shows. We compare it with the current PIM system with isolated memory space. We first compare the performance of CPU task. Current system have 22% performance degradation because the interleaving is switched off, and YunPIM have negligible degradation because CPU page is still interleaved. Well, for PIM task, compared to the current PIM system, we can achieve 1.96 times speed up. Thus, we eliminate the data transfer between CPU and PIM space. This is the summary. The YunPIM can achieve the 3 key advantages. First one is the uniform and shared memory space for both CPU and PIM pages. The second one is fast and transparent data layout by dynamical address mapping. The third one is there is no modification on the CPU side, so it's full compatible with the current CPU system. Then is the second first step. We accelerate a HTAP database with DRAM-based PIM. I will first introduce the HTAP database. This database is designed to support 2 different processing sets. On the left is the OLTP. It do transactions with row-wise accesses. On the right is OLAP. It runs column-wise queries to analyze the columns. So they have different ideal format. So we face a problem we call the format conflict. If you choose a row store, you penalize the OLAP and vice versa. The research community have identified 3 goals for an ideal HTAP. The core challenge is that achieving all the three simultaneously is nearly impossible because the format conflict. The PIM system gave us an opportunity to solve the format conflict problem. We utilized the different access pattern of the CPU and PIM. As we introduced in the last work, the CPU access is interleaved and the PIM is localized in the same bank. The difference is that in the last work,用PIM, we regarded as a conflict and try to solve it. But in this work, we think of it as an optimistic factor and use this divergence to solve the data format conflict. The CPUs across device access and the the PIMs inside device access can construct a 2D access. These slides connect the two dots. The format conflict of HTTP and the 2D access of the PIM system. The OLTP's row-wise operation perfectly matches the CPU's AD access, and OLAP matches the PIM's IDE access. So with this insight, we can propose a single instance unified format HTAP. With the 2D access, it can satisfy both row and column operations. So the format conflict is resolved and the three goals is achieved. During the format design, we still faced three challenges. The first one is the data alignment challenge because due to the data table have heterogeneous data types. We also face the last two challenges, and these challenges have much effect on the performance. My colleague will present the solution to the three challenges on March 25th at section 4D. And that's all. Thank you.
For him to hear. Thanks a lot, Elon. There are any questions for Elon? If not, I'm gonna ask one. So I want to ask actually for UMPIM work. Do you hear me, by the way? I don't. Hello? Elon?
Hello. Sorry, I have some echoes in the system. I can't hear you clearly.
There's echo, yes. I don't know how to solve this. Let me, can you hear me now? Maybe a bit better? I don't know how to do that. Let me do it like that. How about now? No, maybe, yeah, mic is on, but there's echo. Let me try to write. Actually, a simple one.
Maybe you can also say the question.
So my question was in UMPIM, as far as I understand, there's some sort of modification to RCD to make things better. So my question was, is there any routing issue because it's already very dense there? And how would you, is there any problem with that? Yeah.
It's on. It's
Yes, I was asking this part.
Okay. Yeah, we have some hardware modules inside the DRAM. Two module is in the RCD and one module is in the DIMM buffer. There's some routing overhead, some latency for the address translation, and we already included the overhead in the experiment, and the latency is we can control the latency inside one cycle, so it's negligible to the address translation.
I see. Okay. Okay. Thanks a lot for the response. Any other question for Yilong? Okay. Thank you very much, Yilong. Thanks a lot. So we will have the next edition in ISCA. So it's online. The call for papers, actually, invited talks are online. Feel free to submit your work or your ongoing work, any other sort of work that is related to memory-centric systems. We are welcoming them. And this will be full day, so it will be a lot of content, hopefully. And if you missed this, don't worry, there is one more in ICS. 10 days, 10 days later. So I'll need to travel a lot. But this will be not the invited talks, but it will be call for papers. So we will calling for extended abstracts for 2-page extended abstract. This will be in the proceedings. So that will be maybe good for you as well. Yes. This is ICS International Conference on Supercomputing. That will be in July 6th in Belfast, in UK. And that will be again full day. So there are a lot of slots for you to present. And for now, that's 2 more, but we'll never know for more. So, and thank you for attending and all your attention. Hope to see you in ISCA or ICS. Thanks a lot.